Yeah, hello everyone. So
Hello
I
everyone.
think
So I think
it's
it's
6 already.
six already. So uh,
We can start now.
we can start
So
now.
before
So
going
before
are you
going,
able to hear me?
are you able to hear me?
Yes, sir.
Okay.
Okay.
Thanks.
Thanks.
So
So
this is I
this
think
is I think
your week
your
one
week
for your
one for your
NPTEL registered
NPTEL
course has been
registered course
already
has been already
been out.
been
I
out.
mean you've
I
been
mean, you've
accessing
been
your NPTEL
accessing your
portal for
NPTEL
this
portal for this
course,
course,
and
and
I think
I
the
think
lectures
the
and
lectures and
with assignment is
with
already
assignment is
uploaded there.
already
So
uploaded there.
this is your
So this is your
tutorial session
tutorial
or
session or
problem solving
problem
session.
solving session.
So
So
I'm Arifat. So
I'm Arifat.
I will
I
be
will be
here to
here to
conduct these sessions
conduct
for
these sessions for
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 8 weeks.
8 weeks, or
Actually, it is
actually
nine
it is
weeks in total.
9 weeks in
So
total. So
we'll
we will
go
go
every week. There will
every
be
week
a
there will be
session
a
like this
session like this
around this time. So
around
this
this
time
time.
is
So this time
fixed.
is
So that
fixed.
will be
So
every
that will be
Friday,
every Friday
6
from
p.m. onwards.
6 p.m.
So
onwards.
it would be
So it would be
like a
like
2 hour session.
2 hour
So
session. So
so so your
so
courses
your
is
courses
mathematical
is
methods one.
mathematical methods one.
Your ID
Your
is
ID
NOC
is
24
NOC 24
PH02,
PH02,
and your course
and your
instructor
course
is
instructor is
Professor Aditya sir.
Professor Aditya
So
sir.
I guess
So
you are
I
already
guess
aware
you
of
are
this,
already aware
and
of this,
you've been
and
accessing
you've been
this
accessing this
lecture because
lecture
it's already
because it is
started.
already
I
started.
think it started
I
from
think it
22
started from
onwards.
22
So
onwards.
this is your week
So
one,
this is your
and
week one, and
we'll talk
we'll
about
talk about
the
some of
specific
the specific
questions
questions
of linear
of
algebra. So
linear
linear
algebra. So
algebra was
linear
the topic
algebra was
that
the
was
topic that was
started, and
started, and
we'll particularly
we
see
will
some
particularly see
important
some
topics
important
and
topics,
some
and
relevant
it's some
problems.
relevant problems.
And
And
so the target of
so
this
the
session
target
is
of this
basically to
session is
solve
basically
as
to
much
solve
problems
as
as we
much
can,
problems
and
as we can. And
on top of that,
on
like
top
if
of that, like if
any
there is
additional
any
questions
additional
or
questions
any
or
kind of
any
doubts,
kind
so
of doubts,
would
so we
try
would
to
try
rectify
to
and clarify
rectify
them
and
at
clarify
this
them
place,
at
and
this place,
every
and
week we will do
every
that.
week we will do that.
So
So
uh,
uh,
eh, yeah, so
yeah,
that
so
is basically the
that is
thing for
basically the
this
thing for this
sessions.
sessions.
So
So
this will
this will
go
go
for more
for more
7 or 8
7 or
weeks.
8 weeks.
So
So
we will
we
be
will be
doing this
doing
way.
this
So
way. So
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 so is there
so is
something
there
like
something like
if you
if
people
you
want
people
to say
want to
something
say
on
something
this,
on this,
comment link,
comment like,
please you can.
please you can.
Are there any
Are there any
questions?
questions?
No, sir. You can start the class.
Oh, okay.
Oh,
If
okay.
not,
If
then
not, then
well, we can
we
start.
can start.
So
So
so this is
so
your
this is your
linear
linear
algebra
algebra
uh, chapter
chapter,
which was
which was
started this
started
week.
this week.
So
So
so the
so the
basic
basic
outline or
outline
some of
or
the
some of the
specific
specific
topics that
topics that
I will
I will
be
be
doing
doing
problems on
problems
them
on them
would
would
be
be
your what
your
is
what is
vector
basically vector
spaces. That
spaces.
is
That is
what you
what
start
you
with
start
in
with
linear
in linear
algebra,
algebra,
and
and
basis in
basis in
dimensions and
dimensions, and
linear
linear
independence in a
independence in a
product and
product and
orthogonality.
orthogonality.
So these
So
are some
these are some
particular
particular
topics like
topics,
we'll be
we'll be
looking into
looking
their
into the
problems,
problems, and
and we will
and
also
we will
see
also see
I think
I
your
think your
assignment is
assignment is
also out.
also out.
So
So
maybe from
maybe from
next time
next
onwards
time
we can
onwards we
also
can also
discuss
discuss
each week's
each week's
assignments, like
assignments, like
some
some
relevant
relevant
problems that
problems that, like
if you
if
are having
you are
any
having any
difficulty or
difficulty
something,
or something,
we can do
we
that.
can do that.
So
So
so like
so
here
here
so here
so here
basically
basically
in each
in
of
each
these
of these
sections, like I
sections,
will
I will
give a
give a
basic
basic
definition.
definition.
I think
I think
you have
you have
already
already
went through
went
those
through those
lectures which
lectures
is
which is
already been
already been
uploaded on your
uploaded on your
portal.
portal.
So but
So but
just
just
to
to
refresh your
refresh
memory,
your
like I
memory,
will
like
be
I will
giving
be
a
giving
slight
a
hint of
slight hint of
the
the
definitions or
definitions
whatever
or
the
whatever the
basic idea
basic
of that
idea of the
topic is, and
topic is,
then
and
we'll
then we'll
present some
present some
questions here,
questions
and
here, and
we'll
we'll
together
together
try to
try to
figure out their
figure out their
solutions.
solutions.
So
So
vector
so vector
space.
space.
So vector
So vector
space
space
is the
is the
point
point
you start
you start
understanding what is
understanding what
linear
is linear
algebra.
algebra.
So you
So
first
you first
try to
try to
understand what is
understand what
vector
is vector
space.
space.
So
So so
here it is.
here it is.
A vector
A
space
vector
V
space V
over
over a
a F
field F
is a
is
set
a
on
set
which
on
the
which the
following
following
operations are
operations are
possible.
possible.
So
So
uh,
Um,
so like
so like
this
these definitions
definitions
or this
like
or
I mean
I
I
mean
could be
I
like
could be like giving a
slightly a
slightly a
different
different
modified
modified
version of
version of
definition. I mean
definition. I mean
modified version.
modified version.
I mean the
The
language could be
language could be
modified, but
modified, but
the idea
the idea
is all
is
the
all
same,
the
like
same,
which
like
is
which is
been
been
taught in the
taught in the
classes.
classes.
So
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 the reason
the
I'm
reason
giving
I'm
up here
giving up
because
here because
maybe at some
maybe at
point
some
like
point like
while
while
figuring out
figuring
courses
out
by
courses by
solving out the
solving out the
courses,
courses,
we may
we
need
may
some
need some
like
like
a hint
a
of
hint
idea
of
what
idea what
was
was
like
like
logic behind
logic
or the
behind or
reason.
the
So
reason.
for
So
that
for that
sake, I have
sake, I have
put those
put those
like a
like a
brief
brief
idea about
idea
that
about that
topic,
topic,
and
and like I mean like
related to
related to
that,
that
we would
we would
solve the
solve the
questions.
questions.
So
So like
so
so
as I
as
was
I was
telling, a vector
telling,
space
vector
V over
space
a
V
field
over a
F
field F
is a set
is
of
a set
the
of which
following
the following
opposites are
opposites are
possible.
possible.
So a
So
field
a
F
field F
is like
means like
some
some
like a
like
it is a
it is a like
field at
field at
on each
on
and
each and
every
every
point, like
point, like
is
is
something like a
something like
state
a
is
state is
defined, like
defined, like
or like
or like
you can
you
think
can
of
think
like
of
it's
like it's like
a real
a
number
real number
space or a
space or a
complex number
complex number
space.
space.
So
So
like
like
you would
you would
see a
see a
complex number
complex number
space is a
space is a
collection of
collection of
a
a
huge
huge
collection of
collection of
complex
complex
numbers.
numbers.
So that is
So that is
basically you
basically
can
you
think of
can
like
think of
because a
because
vector
a
space
vector
is
space
always
is always
defined
defined
over some
over some
field
field
space.
space.
So
So
like
like
a real
a
number
real number
space.
space.
So I
So
think
I
you
think you
might have
might have
seen them
seen
during
them
your
during the
lectures.
lectures.
So
So
so these are
so
the
these
some
are the some
properties that
properties that
they
they
need to
need
hold
to hold
in order
in order
to
to
call
call
themselves
themselves
a
a
vector space.
vector
So
space. So
like,
like
the
the
first
first
few of them,
view of
like
them, like
they are
they are
like
like
the
the
addition
addition
uh,
uh,
properties, and
properties,
the
and
others
the
are
others are
scalar scalar
scalar
multiplication
multiplication
properties.
properties.
So
So
so like
like
this is
this
your
is your
the first
the
one is
first one
V1
is
plus
V1
V2
plus V2
in V
in V
uh,
is
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 like this is the
this is the
closure property.
closure property.
So if
So if
V1 and
V1
V2
and
are
V2 are
some
some
vectors of your
vectors of
vector
your
space
vector space
V,
V,
then
then
V1 plus
V1
V2
plus V2
has to be in
has to
that
be
same
in that
vector
same vector
space. So
space.
that
So that
satisfies your
satisfies
closure
your
property.
closure property.
And V1
And
plus
V1
V2
plus
equals
V2
to V2
equals to
plus
V2
V1.
plus V1.
This is your
This is your
commutative property.
commutative property.
And
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 and the
and
other
the
is the
other is the
associativity.
associativity.
And I guess
I
like
guess like
you
you
know them
know them
already.
already.
So
So
and this is
and
the
this is the
uh, identity element
identity element
property,
property.
and the
And
same
the
goes
same
for
goes for
the scalar
the scalar
multiplication as well.
multiplication as well.
So
So
so I hope
so I
like the
hope like the
basic idea of
basic idea
vector
of
space
vector
is clear
space
to
is
you.
clear to you.
So
So
is there
is
anything
there anything
you want to
you want
speak
to
or you want
speak
to
or
say
want to say
something?
something?
If not,
If
then we
not,
can
then we can
move with that
move with
question.
the question.
Yeah.
Yeah.
Is there
Is
something
there
to say?
something to say?
No, sir, you can continue.
Oh, okay.
Oh, okay.
So yeah,
So yeah,
the first question
first
we can
question like
see
we can
this,
see this
like
like
so that the
so that the
complex number
complex number
C
C
form
form
a R
a
vector
R vector
space
space
over the
over
field
the
of real
field of
numbers.
real numbers.
So
So
so the thing is
the
like
thing is like we have to prove
like
like
how complex
how
numbers
complex
can be
numbers can
treated
be
as a,
treated as
R vector
R
space.
vector space.
So like
So
in order
like
to
in
prove
order to prove
anything
anything
to be a
to
vector
be a vector
space, so
space,
we have
so
to
we have to all just we
need to
need to
show them that
show
they
them
hold
that they
these
hold this
properties.
properties.
So
So
once they
once
hold
they
all these
hold all these
properties, they
properties, they
after
after
that like we can
like we
call
can call
those as
those
vector
as vector
spaces. So
spaces.
that is
So
what
that is what
we need to
we
do
need
here.
to do here.
So
So
like so like any case
any
like
case
how
like
to
how
start,
to
like
start, like
someone can
someone
turn
can
up and
turn
say
up and
something
say
like
something
if
like
they
if
are
they
already
are
familiar,
already
like they
familiar,
can
like
also
they can
say.
also say.
If not,
If not,
like we
like we
can
can
do right here.
do right here.
So
So
say
say
complex number,
complex number,
basically like
basically like
any
any
complex number,
complex number,
we
we
denoted
denoted
it by
it by
something Z,
something Z,
which has
which
a
has
real
a
part
real part
in the
in the
imaginary part.
imaginary part.
So
So
what you
what you
need to show
need to
here
show
is
here is
like you have to
you have to
prove this
prove this
uh,
uh,
this
this
complex plane,
complex
sorry,
plane,
this
this
complex
complex
vector
vector
space
space
that
that
they have
they have.
uh,
Uh,
I mean
I mean,
its
its
elements or
elements
its
or its
vectors
vectors
basically
basically
satisfied. So there
satisfied.
are
So there are
uh,
uh,
so this
this
Z1,
Z1,
Z2,
Z2,
Z3,
Z3,
so
so
so on.
so on.
So
So
this
this
actually this
actually
vector
this vector
space,
space.
uh,
Uh,
this is
this
we
is
need
we
to
need to
prove that
prove
this is
that this is
some
some
R vector
R vector
space.
space.
So
So
in order to
in order to
prove them,
prove
so
them,
just
so
as I
just as
said,
I
like
said,
you are
you
just need
just
to
need to
satisfy these
satisfy these
properties.
properties.
So
So
let's say
let's say
going with the
going with the
first one,
first one,
like the
like the
closure
closure
property.
property.
So
So
you would
you would
say
say
closure,
closure,
like
like
for
for
closure you
closure
need
you
to
need
show
to show
Z1 plus
Z1 plus
Z2.
Z2.
Uh,
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 I
I
can
can
let me
let me
yeah, this
yeah,
is a
this is the uh,
so this is
so
a
this is a
complex vector
complex vector
space.
space.
So
So
so if
so if
Z1 and
Z1
Z2
and Z2
belongs to
belongs to
uh, this
this
complex vector
complex
space,
vector space,
then the sum
then the
of this
sum of this
Z1 plus
Z1
Z2
plus
should
Z2
also
should also
belong to this
belong to this
complex
complex
vector space.
vector space.
So for
So for
Z1
this
plus
Z1
Z2,
plus
we can
Z2, I
write
can write
x1
x1 plus
I by
I
1
by 1
plus
plus
x2
x2
plus I
plus
by
I
2.
by 2.
So
So
that I
that
can
I can
further write
further
it
write
as
it as
x1 plus
x1 plus x2
I
I
y plus
y1 plus y2.
and
And
so
so so
this
this I can
just
just
simply
simply
call this
call
as
this as
something
something
like
like
a
a
let's say
let's say
um,
um,
a
a
plus
plus
ib.
ib.
So
So
now you
now
see
you
like
see
this can
this
be
can be
uh,
uh,
this
this
z
z.
let me
Let
say
me
this
say this
z3 is
Z3 is
uh,
uh,
this is
this is
this can
this
be
can be
z3.
Z3.
So
So
what I mean
what
to
I
say
mean to say
like
like
this
this
z1 z2
Z1
like
Z2,
we
like we
said that like
said
they
that like they
belong
belong
to
to
some vector
some
space
vector
that
space,
is the
that is the
complex vector
complex
space.
vector space.
So they are
So
the
they are the
vectors,
vectors,
and
and
on doing
on doing
operations on
operations
them,
on them,
like
like
we need
we
to
need to
show that
show
like
that like
they should be
they
the
should
first
be the first
property is that
property
we
is
need
that
to
we
show
need to
them that
show
they
them
are
that they
closer
are
under
closer under
addition.
addition.
So
So
to what I did,
what I
like
did,
I
like
took
I took
any two
any two
vectors,
vectors,
Z1 and
Z1
Z2,
and Z2,
and you just
and you
add them
just
and
add them,
you
and you would
see that like
see that like
the
the
addition is
addition is
also
also
belong to that
belong to
set
that
or
set
that
or
vector
that
space.
vector space.
So
So
I mean
I mean
this is for
this
the
is for
addition,
the addition,
and like the
and
same
like the
you can
same
do
you
for
can
the
do for the
scalar
scalar
multiplication,
multiplication.
and
And
likewise you
likewise,
just
you just
own and check
own and
other
check other
properties. The
properties. The
second was
second was
on
on
associativity.
associativity.
So the
So the
so this
so
was
this
the
was the
closure
closer
for
for
associativity.
associativity.
You just
You
simply
just simply
uh,
uh,
need to solve
need to solve
Z1 plus
Z1 plus
Z2
Z2
plus
plus
Z3
Z3
uh,
uh,
is
is
let me
let
take
me
this
take this
x1
x1
plus
plus
iy1
I by 1
plus
plus
x2
2
plus
plus
iy2
I by 2
uh,
uh,
plus
plus
x3 plus
x3 plus I
iy3.
by 3.
So
So
that I can
that I can
write it as
write it as
uh,
uh,
x1 plus
x1 plus
x2
x2
plus
plus
x3
x3
plus
plus
i
I
y1
y1
plus
plus
y2
y2
plus
plus
y3,
y3.
and or I can right then
right
as well.
then as well.
So this
So
is
this is
basically
basically
uh,
uh,
your
your
associativity
associativity
property.
property.
So don't
So don't
get
get
confused with
confused
this
with this
Z3 which I
Z3 which I
denoted here.
denoted
So
here. So
this can be
this can
something,
be
let's
something,
say
let's say
some other Z.
some other jet.
Like let me say
Let me say
this is some
this is some
uh,
uh,
Z prime.
jet prime.
So this
So
Z
this
prime
jet
also
prime also
belongs to
belongs to this
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 complex
complex
vector
vector
space.
space.
So like
So like
for this
for just
to
to
avoid this
avoid this
confusion of
confusion
this
of
notation,
this
so I'm
notation,
just
so I just
writing this Z
writing this
prime.
jet prime.
There's nothing
There's
else.
nothing else.
And
And
so
so
yeah,
yeah,
after
after
associativity, like
associativity, like
then you
then
can check
you can check
one more,
one
like
more, like
this
this
commutative.
commutative.
So for
So for
commutative,
commutative,
the
like the
commutative,
commutative,
the same
the
thing will
same
go.
thing will go.
So I think
So I
you
think
can
you can
figure out like
figure out like
the
the
way I did
way I
for
did for
associativity.
associativity.
Maybe
Maybe
the next you
the next
can
you
try
can
for
try for
the
the
neutral element.
neutral element.
So
So
for neutral
for
element,
neutral element,
since we are
since
doing
we are doing
addition, so the
addition, so
neutral
the
element
neutral
is
element is
obvious that like
obvious that like
we can
we can
select, we
select,
can
we
choose
can
a
choose a
neutral
neutral
element to be
element
a
to
Z
be a
prime. I
Z
mean,
prime. I mean,
the only
the
way
only way
uh, to assign
to
a
assign
neutral
a
element
neutral element
for the
for the
operation addition
operation
is
addition
zero.
is zero.
So
So
so we
we
have to
have
just
to just
ensure that
ensure
when
that
we
when
do
we
this
do
Z
this
plus
Z
zero,
plus zero,
it gives
it
us the
gives us the
same thing
same
back.
thing back.
So
So
um,
um,
x1
x1
plus
plus
um,
um,
yeah.
yeah.
So I did
So I did
Z1 plus
Z1
0, so
plus zero, so
that is Z1.
that is Z1.
So
So
and when
and when we
we say that like
say that
there
like there
exists
exists
and a
a
neutral element
neutral
or
element
the
or
identity
the
element,
identity element,
uh,
uh,
and the
and the
at the same
at the
time
same
we
time
also
we
should
also should
notice that like
notice that like
this
this
identity element
identity element
comes with
comes
a
with the
inverse
inverse
property.
property.
So
So
when we are
when we are
doing the
doing the
operation with the
operation with the
identity element
identity element,
and
and
it is
it
giving
is
us the
giving us
same
the
element
same element
back,
back,
so that
so that
we can
we
also
can
show
also
that
show that
there also
there also
exists a
exists a
inverse element
inverse element
in which we
in which we
can say
can
that
say
like
that like
or doing
or doing
operation with that
operation with
inverse
that
element
inverse element
will give
will
us
give
this
us
identity
this
element
identity
back.
element back.
So for
So
this we
for
can
this we
have
can have
inverse element
inverse element
that
that
can
that
be
can
like
be like
taken
taken
as
as
minus
minus
g1.
g1.
So if
So
I
if
do
I do
z1
z1
plus
plus
let's say
let's say
if the
if the
inverse element
inverse
is
element is
something
something
g
g
uh,
uh,
let's say
let's
z
say
naught,
z naught,
then
then
it should
it should
give us
give us
0.
0.
0 is our
0 is our
identity
identity
element.
element.
So
So,
so
so
if people are
if you like
getting no,
getting no,
so are you with
so
me?
are you with me?
Yes, sir.
Okay,
Okay,
thanks.
thanks.
So
So
Yes, sir.
yeah,
yeah,
okay.
okay.
So so as I was
As I
telling
was
you, so
telling you,
if
so if
you
you
if you found
if you
a
found a
identity
identity
element,
element,
so at the same
so at the
time
same
you
time
also
you
have to
also have to
ensure that
ensure that
there also
there
exists
also
a
exists a
inverse element
inverse element
in which
in which
when you operate, when you do
when
the
you do the
operation
operation
of the
of the
inverse
inverse
element
element
with
with
any other
any
element,
other element,
you will find
you
that
will find that it will
I mean for
I
every
mean
each
for
element there
every
exists
each
an inverse
element there
element
exists an inverse element
within that vector
within
space.
that.
So
So
when you
when
operate
you
them
operate
together,
them
so you will
together,
find
so
you will get
you will
this
get
identity
this
element.
identity
That
element.
is
That
what I
is
am telling.
what
This
I am
is
telling.
Z
This
not
is
to be
Z
the
not to be the
inverse element of
inverse element of
Z1.
Z1.
Then
Then
you will get
you
this
will get
zero,
this
which is your
zero, which
identity
is
element.
your identity element.
So how can
So
you
how can you
like
ensure that like
you can
you
say that
can
if
say
Z
that if
naught
Z
is
naught is
um,
uh,
let's say
let's say
minus Z,
minus of Z1,
uh,
uh,
that is
that is
um,
um,
minus
minus
Z1
Z1
is
is
minus
minus
x1
x1
uh, minus y1.
y1.
Then if we
Then
do
if I
this
do this
z1
z1
plus
plus
z0, that
z0,
is
that is
basically
basically
um,
um,
x1 plus
x1 plus
i1
y1
minus uh, or so so the inverse element, so this will straight away will give you zero. So the this way you can ensure that like the inverse element for this uh, complex number is just negative. So so the way I did this for the addition, the same you can do for the multiplication, scalar multiplication, because it has other set of properties similarly which follows like for addition, that is scalar multiplication. So like for scalar multiplication, the same thing, you have to start with the closure property under a scalar multiplication. Let's say if you call this fourth property, if you have a some scalar say alpha, so this alpha basically belongs to the field f. So in this case the field is the complex one, the complex number space. So let me write, because we are working on a complex number space. So when you uh, multiply this alpha with this uh, with the vector belonging to the complex vector space, then you see uh, so this belongs to this complex since your alpha x1 alpha y1 uh, belongs to oh sorry, so this will be your real, because uh, so here I told you that this scalar is some like it is your basically some factor from your or just a number that comes from your field f, which I was telling you f. So for this, for here, your field be real number space. It won't be, I mean, I mistakenly told you that this will be complex one. That won't be a complex number space. That is basically your real number space. So I was talking about this property. So yeah, so that is how you prove like closure under scalar multiplication, and then likewise you can also so like rest other properties. Uh, like the next one is the linearity property. This one, this so this also you can so easily. Let me do it quickly. This alpha. So I can write this as alpha z1 plus z2. Sorry, x1 x1 plus x2 plus I alpha y1 plus y2 and alpha x1 plus alpha x2 alpha y1 alpha y2. So that I can simply write this as alpha g1 plus alpha g2. So that
So
satisfies
that
your
satisfies your
linearity,
linearity,
and then
and then
um,
um,
there is
the,
this
this
identity element
identity
property.
element property.
So here,
So
like
here,
you
like
can
you
just
can
see
just
that, like
see
for
that, like for
scalar
scalar
multiplication, the
multiplication,
identity
the
element
identity element
has to be
has to
one
be
possible
one
case,
possible
that is
case, and that is
multiplying it with
multiplying it
one.
with one.
So one will
So
be your
one will be
identity
your
element,
identity element,
or the
or
neutral
the
element
neutral element
property,
property,
and then
and then
there was also
there was
one
also one more
property which I
property
missed
which
here.
I missed here.
So it is
So it is the
alpha one,
alpha one,
alpha two,
alpha
something
two,
like
something like the,
that is
that
alpha
is alpha
alpha one,
alpha one,
alpha,
alpha,
I think,
I think,
yeah,
yeah,
alpha one,
alpha one,
alpha two.
alpha two.
We so
So
likewise, like the
likewise,
same
like
we
the
did
same
for
we did for
um,
uh,
vector addition.
vector addition.
This I
This
mean
I mean the
the
for the
properties
properties
under addition.
under addition.
So the
So
same you
the
can show
same you
for
can show for
these
the these
properties. You can prove
properties. You
these
can prove
properties
these
for
properties
scalar
for scalar
multiplication. So
multiplication.
like,
So like
uh,
uh,
so are
so
you able
are
to
you
follow
able
this?
to follow this? Like
So is there
so
any
is
doubt?
there
Like,
any doubt? Like
is there
is there
anything
anything
like that
like
you
that you
could not follow
could
here?
not follow here?
Yeah.
Yeah.
Actually, I joined it, so could I just get a quick glance over it before you scroll it down?
Oh, okay.
Oh,
So
okay.
like,
So like
I just
I just
didn't do much.
didn't
I
do much.
just
I
was just
like I was just
explaining.
explaining.
Like I was
Like
talking
I was
about this
talking about
question.
this question.
So there is a
So there is
complex
a
number
complex number
vector space,
vector space,
or like
or like
what I was
what I
trying
was
to prove
trying
here.
to prove here.
Like you can
Like you
prove
can
complex
prove
number.
complex number.
They actually
They
form
actually form
a real
a
vector
real
space.
vector space.
A,
They
they form a
they
real
form a
vector
real
space.
vector space.
So in
So
order to
in
prove
order
them
to
as a
prove them
real
as a
real vector
real
space,
vector space,
so
so
you
you
have to just
have to just
obey these
obey these
conditions.
conditions.
So
So
for this
for
to
this
obey these
obey these
conditions,
conditions,
like you have
like
to
you
work
have
out,
to work
or
out,
you have to
or
check
you have to
each of
check
these,
each of this,
like whether
whether
they are able
they are
to
able to
hold these
hold these
properties or not.
properties or not.
So if they are
So if they
following
are
these
following these
properties, after all,
properties, after all,
at the end
then
of the
at the
day,
end
they
of the
will
day,
form
they
a
would form a
vector space.
vector
So that
space.
is
So
the
that is
basic
the basic
idea about
idea
vector
about
space.
vector
So
space.
that is what
So
we
that is
are
what
doing
we
for
are
this
doing for this
complex
complex
thing also.
thing also.
So we know a
So we know
complex
a
number
complex number
is basically
is
denoted
basically
by
denoted by
g equals to
g
x
equals
plus
to
i.
x plus I, iy.
So and
So
we
and we
say that, like,
say that,
there
like
exists a
there exists a
complex
complex
set
set
of
of
G1, G2,
G1,
G3
G2, G3
of
of
many such
many
elements,
such elements,
and
and
we want
we
to
want
say
to
that
say that
they are
they are
um,
um,
these
these
elements, they form
elements, they form a
a real vector
real
space.
vector space.
So
So
to show that,
to
like,
show
we
that,
have
like
to
we have
prove
to
all these
prove all these
properties,
properties,
Z1 plus
Z1 plus
Z2,
Z2,
and
and
this will be
this
your
will be your
closure under
closure
vector
under
addition,
vector
and this
addition,
will
and
be
this will be
associativity, and
associativity,
this is your
and this is
neutral
your
element
neutral
property.
element
So
property.
all these
So all
properties,
these properties,
I have showed
I
some
have
of
showed
them, and
some of
you
them,
can
and you can
see for
see
others
for
also.
others also.
So that is what
So
I
that
was
is what I was
speaking here.
speaking here.
Right. Thank you, sir.
Okay.
Okay.
So anything
So
more, like
anything more, like
if someone has
someone
anything,
has anything
like
like
they had any
had
problem,
any
or
problem,
they
or
had
they
any
had any
difficulty
difficulty
in knowing
in
these
knowing
things,
these
like
things,
they
like
can
they
speak.
can speak, like
So
so. So
I hope
I
it
hope
is clear
it
for
is clear
everyone.
for everyone.
So
So
is it clear for
is it
everyone?
clear for everyone?
Yes, sir.
Okay.
Okay. So
So if it,
if it,
so if it is clear
so if
for
it is
everyone,
clear
then
for
fine.
everyone,
We
then
can
fine. We
move on
can
with
move
the
on with the
next
next
person.
person.
So
So
yeah.
yeah.
So now
So now
this
the
question is
this
about,
question is about,
you have to
like
show
we have to
a n
show
degree
a n
polynomial
degree
how they form
polynomial,
a
how they
vector
form a
space.
vector
So
space.
the
So
question is
the
like this:
question
the
is
set
like
of
this: the
all
set of all
polynomials of
polynomials
degree
of
n
degree n
form a vector
form
space
a
of
vector space of
dimension n
dimension
plus one.
n plus one.
So
So
let P a
let
denote
P a
a
denote a
polynomial in the
polynomial in
variable
the
x
variable x
belonging to R
belonging to
of
R
degree
of
n.
degree n.
So
So
let's say we have a
let's say we have a
polynomial P a.
polynomial
So that
P a.
is
So that
P
is P
a,
a,
which is which is n
which is
degree
an n degree
polynomial,
polynomial,
which can be
which can be
shown like this,
shown like this.
and
And
and they uh, and they form a vector space over a like they form a real vector space like how we were doing for the previous question that a complex numbers like they eventually can be constructed eventually they can construct a real vector space. So that is what we will see. And degree polynomial can also a family of n degree polynomial can also form a real vector space, just like how we saw earlier, like a set of complex numbers can form a vector space, a real vector space. So the the question here is like so that above addition and scalar multiplication uh, rules imply the following comparison rules in Pn. So so the I mean mm, the addition and scalar multiplication rules are basically these two are addition and scalar multiplication rules. So um, so the addition like you basically uh, you have to do like I mean these are the same addition or scalar multiplication rules which you like which I was telling you about these conditions. This additions and scalar multiplication rules. So again, we have to check the same thing back there also for the polynomials. So uh, like this thing is like you you take a polynomial. I mean like here as you can see here, this is your polynomial, and you can say that like yeah, for every different values of a0 a1 these coefficients a0 a1 and you you can construct a new set of I mean construct a new polynomial. So each time you pick a different values for them, you can construct new polynomials, and this actually a0 a1 a1 and this all comes from your uh, real numbers. These are basically they belong to real set. So so that is what I am showing here. Like under addition, you will see that like you take those elements from there, and after adding them, you will find that they will again belong to the same real vector space. So uh, so this is that we have two polynomial PA, PB, and after addition they may take this form. So this is basically, let's say if I have a polynomial uh, f of x1, and uh, I can uh, yeah a0 mm, a0 x1 to the power uh, a1 uh, x1 plus a2 x1 square. So and if I have another polynomial g of x2, or I mean this has to be x1 only. In this case I have a0 prime x1 plus a1 prime x1 plus a2 prime x1 square. So I can show that like h of uh, x1 is basically mm, uh, a0 plus a01 x1 plus so, So
So
this is
this is
basically
basically
like
like
what I did.
what I did.
I
Like
mean,
I mean,
initially,
initially,
uh,
uh,
as you were
as you
denoting
were
your
denoting
function
your
as f
function
of
as f
x.
of x.
So
So
after
after
the addition,
the addition,
this is
this is
basically
basically
uh,
uh,
uh, like calling your
calling your
like
like
function as,
function as,
let's say,
let's
if
say,
I
if
can
I can
write this
write
in
this
this
in
form,
this form,
like
like
I mean,
I
what
mean,
I
what I'm
mean to say,
mean to say, like
maybe like we
maybe like
can
we can
sharply work this
sharply
out.
work this out.
Let's say,
Let's say, let's
the basic
the
idea is
basic
like we
idea
have
is
to
like
show
we have to
something
show
like this.
something like this.
We have to show
We have to
something
show
like this.
something like
If
this.
we have
If we have
f of x1
f of
and g
x1 and g of
of x1,
x1,
so like
so
maybe
like maybe
we can
we can
work this
work this
out
out
properly here.
properly here.
Let me
Let
clear
me
this out
clear
here.
this out here.
So
So
yeah,
yeah,
so uh,
uh,
we have
we have
PAX
PAX
plus
plus
PBX.
PBX.
So these are
So these
uh,
are
two
two
different
different
polynomials. Let's
polynomials.
say
Let's say
A0,
A0,
X0. So these
X0. So these
polynomials are of
polynomials
this
are
form,
of
as I
this
said.
form, as I said.
This
This
um,
um,
plus
plus
A1,
A1
X1
X1
plus
plus
up to,
up to,
let's say,
let's
we
say,
have
we have
n degree
n degree
plus
plus
B0,
B0
X0
X0
plus
plus
B1,
B1
X1
X1
plus
plus
Bn,
B1
Xn.
Xn.
So
So that you can
write them as
write them
A0
as
plus
A0 plus
B0
B0
X0
X0
plus
plus
A1 plus
A1
B1
plus B1
plus
plus
AN
An
plus
plus
Bn
Bn.
Xn.
So,
So
so
that is what
that is what
basically
basically
PA plus
A
B.
plus B.
So
So
that was
that
this
was this
uh,
uh,
like
like
thing which we
thing
have
which
to
we
solve.
have to solve.
And
And like
this is for
this
like
is for
the
like the
addition case,
addition case.
like what
Like
happens
what
here.
happens here?
This
This
as I
as
told
I
you, like
told you,
this
like this
A's,
A's
this
this
A's and
A's
B's,
and B's,
they belong
they
to
belong to
this
this
real
real
set.
set.
So after
So after
the for this
for this
polynomial which
polynomial
we
which we
obtain here
obtain here
for
for
PA plus
P a plus
PX,
bx,
after the addition
after
of
the addition of
P of
P of
PAX and
PAX and
PBX,
PBX,
we see that
we see that like
those
those
coefficients are
coefficients
changed
are
to
changed
something
to
like this:
something like
A0
this:
plus
A0 plus
B0,
B0,
A1 plus
A1
B1,
plus B1,
and so on.
and so on.
So
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 these
this
like these
like these
additions,
additions,
I mean
I
this
mean
A
this
plus
A
B,
plus B,
for all,
for all,
initially we had
initially we
only
had only
A's for
A's for
uh,
uh,
PAX
PAX
and
and
B's for
B's for
PBX. And
PBX.
after
And
addition,
after
this A
addition,
plus
this A
B,
plus
you
B,
see that
you
like
see
this
that
A
like
plus
this A
B
plus
still
B still
belongs to this
belongs to this
real.
real.
So
So
this real
this
set is
real set
basically
is
of,
basically
like
of
if you have
like
a
if you have a
n degree
n degree
polynomial,
polynomial,
then
then
this real set
this
will be
real set
n
will
plus
be
1.
n plus 1.
And how
And
this will
how
be n
this will
plus
be n
1?
plus 1?
Basically because you
Basically
see,
because you see,
uh,
uh,
so for
so
this
for this
polynomial P of
polynomial P
x,
of x,
the
the
highest degree is
highest degree
n,
is n,
that is
that is
n.
n.
But
But
you will see
you
that
will see
you
that
have
like you
to
have to
know like
know like
n different
n different
monomials.
monomials.
Like
Like
there are like
there are like
this is
this
like
is like
a0
a0
is
x0
your
is
first,
your first,
like for
like for
is your
is
first
your
term here,
first term here,
that that contains one monomial. That is of course a constant term, but that is the term corresponding to x to the power 0. So then you have the term corresponding to x to the power 1. So and so on till x to the power n. So this whole altogether they form a n plus 1 like a vectors, or like you need n plus 1 independent degrees of freedom to describe this polynomial. So that's why like you need n plus 1 coefficients. So that's why I wrote here n plus 1 uh, real real set. So are you getting? Hello.
But I have a question.
So
Aren't we forcing the n plus one condition because we have chosen that our polynomial starts from degree zero?
sorry, like could you repeat that again?
I mean, like it's like we are forcing the n plus one condition because we are starting our polynomials from the degree zero. If we started them from one, then we would have just n,
Oh, no, no.
right?
Even then, like if you said like if I have a polynomial, let's say f of x, I have like as you are telling, we are missing out that 0 polynomial. Like we would say like I have polynomial ax square plus bx, and even in this case, you need still need uh, like three three vectors corresponding to one here, corresponding to one here, and also the other let's say c x to the power 0, in which c is kept to be 0. So like even if you have f of x is a function without this term, in that case c is like in that case c is 0. So that's why like it is not appearing in your polynomial, but still you can say that that polynomial is will be described by a R3 vector space, because the high this your n is 2, your n is 2 here, but to make this to a real vector space, you need a real vector space which have three independent degrees of freedom. So that's why I wrote R3. So we will understand like these are basically
Okay.
basis vectors and things you have already also studied in your lectures. So you need like three independent linearly independent vectors, or like you can say three basis vectors to span this entire polynomial. I mean this R3 vector space. So I hope like that is clear for you.
Yes, sir.
Okay. So is there anything else like help you with if there is something that went wrong or it didn't go properly? If it is fine, then I can move. Like so, the other thing that we wanted to prove here is this part here. So like the same you can do. So this was like a vector addition. This is the addition property, like to or like what we were calling it as earlier, like closure under addition. This was the property of closure under addition. Now this is was the property of closure under multiplication. So so to check that like how we can do like so uh, you say that you have some alpha belonging to R, and then you do this alpha p x. So that is basically or here I was
here I
taking
was taking
C.
C, so maybe
I should take
I should take
the
the
C.
C.
So now
So now
this
this you can now
call
call
PCA of
PCA
X.
of X.
So this
So this
PCA of
PCA
X
of X
uh,
um,
is the thing
is
that
the thing that
you
you
wanted to
wanted
show
to
here.
show here.
So
So
now
now you see that PCA,
this
this
new
new
coefficients,
coefficients, this
CA,
CA0,
this
this
CA1,
CA1,
and so on.
and so on.
They
They
also
do also
belong to
belong
this
to this
real n
real
plus
n
one
plus
set.
one set.
So that
So
is the
that
thing
is the
like how
thing
you
like how
show
you saw
the
the
closer
closer
conditions like
conditions
for
like for
both
both
operations,
operations,
whether it is
whether it is
addition or
addition or
multiplication. Like
multiplication. Like
they need
they
to
need to
be
be
coming into
coming into
a structure
a
that
structure
like
that
after
like
all
after all
this
this
I mean
I mean
this
these
coefficients need
coefficients
to
need to
belong to the
belong
same
to the
set.
same set.
Like
Like
how
how
as I
as I
uh,
uh,
told you about
told you
this A
about
plus
this A
B.
plus B.
So
So
like earlier
like
in
earlier
this
in
like
this like
polynomial,
polynomial, you only
for this
for this
multiplication
multiplication case
you had
you had
A0
a0 a1 an
all this
all this
belonging
were
to
belonging to
Rn plus
Rn
one
plus 1
set.
set.
Now after
Now after
doing this
doing this
scalar
scalar
multiplication,
multiplication,
so
so
after this
after this
operation you will
operation
find
you will
that
find that
this new
this new
coefficient again
coefficients
has to
again
be
has to be
uh,
uh,
belonging to
belonging
this
to
real
this
set.
real set.
So
So
so that was
so that was
and
that. And
so the
so the
next
next
is the
is
follow-up
a
question
follow-up
to that,
question to that,
and that
and
is
that is
um,
um,
how do you
how do
say
you
that like
say
this
that like this
polynomial
polynomial
um,
um,
under
under
addition
addition and
scalar
scalar
multiplication
multiplication
is a
is a
real vector
real
space,
vector space,
uh, and
and how you can
uh, map that to
map that
R
to
n
R
plus
n
one
plus
vector
1
space. So
vector
that
space.
is
So that
actually
is actually basically
I told
I
you
told
somewhat
you somewhat
right here.
right here.
So
So for
this question
this question,
we
like
just
we just
to
needed to prove
only
only
these
these
conditions.
conditions.
So
So
after that like
after
there
that,
are
like
other
there are other
properties which you
properties
need
which
to
you
also
need to also
satisfy them,
satisfy them,
and
and
so
so
for them you have
for
to
them you have
work
to
out
work out
particularly again
particularly again
like
like
by
by
uh,
uh,
going through
going
this
through this
uh,
uh,
each and every
each and every
uh,
uh,
part of this
part of this
vector space
vector space
definition.
definition.
So
So
like we can
like we
start
can
again with
start again with the
a closer one
closer one,
which is already
which is
the part
already
of
the
the
part of
previous
the
question.
previous question.
So
So
this has
this has
already
already
uh, these two
these
are
two
already
are
done.
already done.
Now you can
Now you can
check the
check the
associativity
associativity and then
commutativity,
commutativity,
and then
and then
also you can
also
go
you can go with
checking their
checking the
neutral
neutral
condition.
condition.
So let's say
So
that
let's say then
for
for
associativity you can
associativity you can
just simply
just
say,
simply say.
so
So
the first
first
one is the
one is
closer
the closer
condition,
condition.
so which
So
is
which is
as
as
proved
proved
previously,
previously,
and
and
the
the
second is
second is
uh,
uh,
associativity.
associativity.
So for
So for
associativity
associativity, what you can do,
you can just
you can just
so
so
mm, I can
I
write
can
this as
write this as P
uh,
uh,
B plus
P
C.
plus C.
Why?
Why?
Because
Because
I can
I
write this
can
as
write this as
B plus
P
C
plus
from
C
this
from this
property.
property.
As I
As I
so as I
so as I
showed you,
showed here,
like
like
P A plus
P A
B
plus
can
PB
be written
can
as
be
P
written as
A plus
P A
B.
plus B.
So
So
So for
So
that
for
reason, I
that
can
reason, I
write
can
A
write
plus
PA plus
P plus
P
C
plus C
in
in
subscript,
subscript,
and then
and then
together I can
together I
write
can write
P A plus B plus C. Like how I'm
how
doing
I'm
this,
doing
like
this,
again
like
the same
again
thing.
the same thing.
So let's
So
say
let's say
call
I
this as
call this
something
as something
P A
PA
plus
plus
some
some
P
P
A
A
prime.
prime.
So
So
I can
I
always
can
write this
always
as
write this as
P
P
A plus
A
A
plus
prime,
A prime,
satisfying the
satisfying the
uh,
uh,
condition as
condition
we
as we did
previously
previously
in the previous
in the
question.
previous question.
So
So
this A prime
this
is
A prime
basically
is basically your
P plus
P
C.
plus C.
So
So
so that
so that
so then
so
again,
then again,
what you do,
what
like
you do, like
you can
you can
write this
write this
P A
P
plus
A
B
plus
plus
B
C.
plus C.
I mean this one
This one
is
is
P A
P
plus
A
B
plus B
plus C.
plus
So
C.
you can
So you
write
can
write in that
write
way.
in
That
that way.
is
So
a
that is a
different way of
different
writing
way
it.
of writing it.
And
And
but when
but
you
when
do
you
this,
do
you
this,
find
you
that you
find
can
that you can
break them
break
apart.
them apart.
PC,
PC,
and that is
that
actually
is
here
actually your
PA
PA
plus
plus
BB
BB
plus
plus
PC.
PC.
So
So
there,
there,
you you have
you have
proved
proved
how this
how this
obey
obey
associativity.
associativity.
So
So
so we
so
started
we
with
started
this.
with this.
So
So
this is what
this
we
is what
wanted
we
after,
wanted after.
and
And
so
so
yeah, and then
yeah,
you
and
can
then
also
you can
see
also see
for this
for this
polynomial,
polynomial,
the Newton
the
element
Newton element
would be
would be
something like
something like
for the
for the
identity element
identity element
case, you can
case, you can
uh,
uh,
or
or
neutral element,
neutral element.
you can
You
have a
can have a
polynomial
polynomial
whose
whose
coefficients all
coefficients
are
all are
set to zero.
set to zero.
Basically,
Basically,
uh,
uh,
so in
so
this
in this
polynomial
polynomial
p of
P of
ax,
ax,
where
where
p of
P
ax,
of ax,
where
where
all the
all the
polynomial a0,
polynomial a0,
a1,
a1,
a2,
a2,
so on,
so on,
an
an
is set to zero,
set to zero,
then that
then that
polynomial
polynomial
will be your
will be your
neutral element.
neutral element.
So
So
and
and
similarly,
similarly, like
for the
for
inverse
the
case,
inverse
you
case,
can say
you
that
can say that
you
you
can
can
um, or this is
or this is
actually
actually
part of
part of
this only.
this only.
So for
So for
inverse,
inverse,
you can
you
define
can define
polynomial
polynomial
minus
minus
ax
ax
uh,
uh,
such that
such that
pax
ax
plus
plus
p minus
b minus
ax
ax
can give you
can give you
um,
um,
um, let me write 0x to the
0 x
power
to the
0
power 0
0
0
x
x
plus 0
plus 0
xn.
xn.
So
So
so that
so
is
that is
so that is
so that
this
is this
polynomial,
polynomial.
basically your
Basically, your
the
the
identity element.
identity element.
So this way
So
you
this
can
way you
prove
can prove
them like
them like
how
how
they would
they
satisfy
would
all the
satisfy all the
properties
properties
of a vector
of a
space,
vector
and
space.
after
And
satisfying
after
all those
satisfying all those
conditions,
conditions, now you
now you can
can
finally
finally
call them
call them
as
as
a vector
a
space.
vector space.
But
But
the thing
the thing
which you
which
need to
you need to
know here,
know here,
like I have
like
showed
I
this
have
for
showed this for
the
the
addition. The
addition,
same you
the
can
same you
work out
can
for
work
the
out for the
scalar
scalar
multiplication for
multiplication for
other
other
cases which I have
cases which
left
I
out.
have left out.
So
So
after showing
after
them,
showing
you can
them,
say
you
that
can
like
say that like
you can
you can
uh,
uh,
say
say
there
there
exists
exists every uh,
there
there
exists
exists
these
these
coefficients
coefficients this
belong to
belong to
real n plus
real
1
n plus
set,
1 set,
and
and
you can
you
say
can say this
um,
um,
x0,
x0
x,
x
x square,
x square
and so on
and
up
so
to
on up to
xn.
xn.
These are
These
basically
are basically your
these
these
monomials are
monomials are
basically,
basically
you
your,
can say
you
them
can
as
say them as
vectors.
vectors.
So you can
So
think
you
of
can
this
think
as
of
an
this is an
n
n
plus
plus
dimensional vector
dimensional
space,
vector space,
where
where
this x0,
this
x,
x0
x
x
square,
x
and
square
x
and
cube,
x cube
x4, and
x4
so on up
and
to
so on
xn.
up to xn,
These are
these
like
are
you're treating
like
them
you're
as
treating them as
like a,
like a,
let's say, unit
let's say
vectors,
unit vectors,
and or
and or
this is what
this is what
you can also
you
call
can
them
also
as
call them
basis
as
vectors.
basis
So
vectors.
they
So
can
they can
generate
generate
an entire
an entire
Rn plus one
Rn plus
dimensional
1
vector
dimension
space.
vector space.
So,
So
this is
so
what
this
you
is what
needed to
you
prove.
needed to prove.
Like it
Like
is
it is
isomorphic to
isomorphic to
n plus one.
n plus
So
1.
if you're not
So if
familiar
you're
with
not familiar with
isomorphic term,
isomorphic
like
term, like
isomorphic means like
isomorphic means like
this is like
this is like
mapping
mapping
like
like
from one
from
set to the
one
other.
set
Like
to the
this
other.
is
Like
like
this
a
is like a
mapping between
mapping between
like two
like
sets,
two
where
sets,
each
where
element
each element
like
like
maps to,
maps
like
to,
this,
like
like
this is like
I think you
I
have
think you have
also
also
been familiar
been
with, I
familiar
mean,
with, I mean,
little bit
little
about
bit about
this
this
what you call
what you call
sets. Like I
sets.
mean,
Like I
there
mean,
is one
there
to
is
one.
one to one mapping.
So this one
So
to one
this one to one mapping is
basically
basically
you call them
you
as
call them as
isomorphic or
isomorphic or
bijective.
bijective.
So this
So this
bijective property,
bijective property, like
shown
this
here, like
shown
this
here, like this
Pn
Pn
polynomial maps
polynomial
to
maps to
this
this
Rn plus one
Rn
vector
plus 1
space.
vector space.
So that is why
So
like
that is why
we
like
call it
we
as
call it as
isomorphic.
isomorphic.
If
If
you
you
are
are
having
having
with
with problem with
isomorphic, then
isomorphic,
it's
then
fine.
it's fine. You
You can
you
just
can just
drop it for
drop
now.
it for
Like you
now.
can just
Like you can
simply
just simply
say
say
n degree
n degree
polynomial
polynomial
can
can
construct
construct
a
a
Rn plus one
Rn plus 1
vector space
vector space
in this
in
manner,
this
because
manner
they
because
satisfy
they satisfy all these
conditions
conditions
which we
which
have shown
we
here.
have shown
So
here.
I hope
So
this
I
is
hope this is
clear to
clear
everyone,
to
or
everyone, or
if not, like
if not,
they
like
can
they can
raise their concern
raise their
if they
concern, like
have
if
any
they have any
problems somewhere.
problem
Like,
somewhere. Like
hello,
hello,
are you able to
are you able
like
to
follow
like
this?
follow this?
Yes, sir.
So fine,
So
like
fine, like
fine with the
fine with the
others as well.
others as well.
If you're not
If
getting
you're not
anywhere,
getting
like, you
anywhere,
can
like you
speak
can
up
speak
and
up and
you can
you can
tell me
tell me
exactly if you
exactly
want to
if you want
repeat
to
something,
repeat
if you want
something,
to
if you want to like
get something
get
more
something more
properly clearly.
properly
You can
clearly.
tell.
You can
Yeah.
tell. Yeah.
In
Following,
the
sir.
like question,
Yeah.
Yeah.
in the question you wrote R tends to R. What does that mean?
Uh, which one?
Which
In the
one in the
question?
question?
Like somewhere here. Yeah, in the PA, R tends to R above that A part,
So you're
So
talking about
you're
which
talking
you have
about this
underlined.
this one?
this one?
No, above that, above the A part.
Oh, PA
PA
R goes to R.
goes to R.
So this
So
means
this
like
means like
we have a
we have a
polynomial,
polynomial,
like
like
what I'm
what
telling.
I'm telling.
This is like we
This is
have a
like we have a
P of
polynomial P
X,
of X,
where
where
in this
in this
polynomial,
polynomial,
like
like
what
as
I
what
have
I have
written here,
written here,
A0,
A0
X0
X0
plus
plus
A1
A1
X
X
plus
plus
so on up
so
to
on up to
nxn.
Xn.
So in this
So in
polynomial,
this polynomial, the
coefficients,
coefficients
they
they
basically
basically
this A0,
A0
A1,
A1
An
and
coefficients,
coefficients,
they
they
belong to
belong
R,
to R,
and we are
and
doing
we are doing
operation on
operation on
PA such
PA
that
such
we
that
are
like we are
like as
like
we did
as we
PA
did PA
plus
plus
PP.
PB.
So
So
the
the
resultant of this
resultant of this
polynomial will
polynomial
also
will
be
also be
something of this
something
form,
of this form,
x0
x0
x
x I mean
x
x
so on.
so
So
on. So
where
where
these
these
coefficients will
coefficients
also
will
belong
also
to
belong to R.
That is what I meant here.
Okay.
So
Okay. Thank you.
yeah, yeah. There's if there's something else, I think like someone else had helped me with the question. Yeah, you can speak like if there's any problem, anything which was not clear, or like all fine for everyone. Okay, if it is all fine, then we can move on. Like there's a message in the chat box. Like Lakshmi Singh, like I think you have written properties of vector space. Uh, like could you like tell me your doubt properly so that Lakshmi Singh.
Hello, sir.
Yeah.
Yeah, sir. Actually, I was trying to solve last few days. I was trying to solve the assignment which was given to us.
Uh-huh.
That these problems I was finding difficulty. The
Okay.
first problem, the second problem. That was the thing. That in those live, recorded lectures which was provided to us, I went through those, and there were some theories as well as examples on meridian of triangle, then two-third value, and then but the question which was given in the first question I could not understand. I could not find the solution of that.
Well,
Means I could not understand the question. Means options are okay,
okay.
but I could not understand the question.
Like as of now, like I don't have that assignment because like I've been told that like I can like we can discuss that assignment. There is no such problem, but we can do it in the next week. So
Okay, sir. But these things which you are showing, it's
mhm.
very good. But these things are also there in those class videos. So yeah,
Okay,
lecture videos. Yeah.
okay. These questions,
Properties. Properties. Sorry, no, sir. I'm talking about properties.
yeah, properties like
Question from
they're already there. Like I think in the lecture videos they should have been discussed. So
yes,
and
yes.
I think that has been discussed, but they have been discussed maybe in a slightly different manner, like the notations or language could differ. But here I have just put up this thing here just for the sake of like relating with the courses that I am presenting here. So so for that reason I have kept it here. But
Yeah.
otherwise, like you can always follow whatever the things has been taught in the
No, no,
lectures.
this is okay. These questions are okay, sir. It
Okay,
is clear now.
okay. But
Yeah.
sure, like we can discuss those questions like from next week onwards. So
Next week.
yeah, yeah, we can do that. So, but
I will come up with the problem, sir.
yeah, yeah. But for now, like, are you having any problem with these questions or anything?
No, these things are clear.
Okay, okay, fine. So so if it is fine for everyone, then we can move.
Yes.
Okay. Um, so the the next is also a follow-up question. So here it is basically telling like find a set n plus one polynomials p a zero to p a n such that uh, that is the part of p n forming a basis for this vector space. So for basically it is asking us to construct a basis for the polynomial which we are mapping into Rn plus vector space. So for Rn plus one vector space, we need n plus one basis. So those bases as I told, uh, this one x x square xn, they form an Rn plus one vector space. So
So
for this
for
Rn
this
plus one
Rn
vector
plus one
space,
vector
you
space,
can
you
say
can say
like for
like for
um,
um,
for like
for like
one you can
one you
define
can
a vector
define a
space,
vector
let's
space,
say
let's say
uh,
uh,
E1
E1
to
to
n,
n,
then
then
E2.
E2.
So
So
this basically
this basically
denotes your x
denotes
to
your
the
x to the
power 0
power 0
vector, and
vector,
this
and
denotes
this denotes
basically your
basically your
x to the power
x to
1
the power
vector,
1 vector,
and so on. You
and
can
so
have
on you can have
E3.
E3.
So that
So
will be
that will be
your
your
execute term.
execute term.
So this way,
So
like
this way,
the
like
basis
the
will be
basis will be
uh,
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 the basis can
the
be
basis can
constructed
be
for
constructed
this
for this
Rn plus
Rn
1
plus
dimension.
1 dimension.
So the thing
So
is
the
like
thing is
you
like
are treating
you are treating
um,
um,
you're treating like
you're
each
treating like
monomer,
each
this
monomer,
x.
this x.
I mean, this is
I
your
mean, this is your
constant term. This
constant term.
corresponds
This
to the
corresponds to the
constant term x to the
constant
power
term x to
0
the
and
power 0
x.
and x.
X. This
X.
I think
This
this will
I
be
think this
your
will be your
x
x
uh,
uh,
x square.
x square.
So
So
these are your
these
like,
are your like
they form a
they form
vector
a
space.
vector space.
Like
Like
so in
so in um
yeah.
yeah.
So
So
using them,
using
you
them,
can
you can
basically
basically
construct this
construct this
polynomial of
polynomial
any
of any
n degree,
n degree,
like by
like by
linear
linear
combination of these
combination of these
monomials.
monomials.
So
So
if you
if you
write a linear
write a linear
combination of
combination of
these
these
monomials up
monomials
to all
up to all
n,
n,
there are n
there are
such
n such
monomials
monomials
altogether, you
altogether,
can write
you can write
a vector.
a vector.
You can
You can
you can write
you can
a
write a
polynomial
polynomial
uh,
uh,
p a
p
of
a
x.
of x.
So basically,
So
this is
basically, this is a
p a x is a linear
PAX is a linear
combination of this
combination of this
basis vector.
basis vectors.
So that is
So
what.
that is what.
So
So
so that is what
so
I
that is what I
already referred in
already
the
referred in the
previous
previous
part also.
part also.
So the next
So
thing
the
is
next
basis
thing
and
is basis
dimension.
and dimension.
So
So
basis and
basis
dimension,
and
like it is
dimension, like
also
it is also
already been
already been
told to you
told to you during
in your
in your
lectures.
lectures.
So
So
here, like
here,
just
like
to
to
make you
make
remind
you
like
remind like
what
what
basis and
basis and
dimension is
dimension is
all about. Like
all about.
whenever
Like
we
whenever
write
we
some
write
vector
some
space,
vector space,
we
we
denote a number
denote a number
like
like
on this
on this like
on the
on the
like
like
you can
we can
understand like there is a
understand like there
number
is a number
on top of
on top
this
of this
bold letters,
bold letters,
on the
on
script
the
letters.
script letters.
So this
So
letters
this
actually
letters
basically
actually
denote
basically
this
denote this
dimensions,
dimensions.
and
And
so
so
basically dimensions
basically
are the
dimension
number
are
of
the number
components
of components
required to
required
specify
to
a vector.
specify a vector.
Uh,
Uh,
um,
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 uh,
uh,
mm,
um,
like
like
to I
to
mean
I mean
like
like
that is
that
basically
is
the number
basically
of
the number of
basis vectors
basis
that is
vectors that
required
is
to
required to
construct a vector
construct a
space.
vector space.
So
So
like as we
like
were
as
doing
we
in
were
the
doing in
previous
the
case, we
previous
were
case, we
writing
were writing
for
for
polynomial
polynomial
vector space to
vector
be
space
r
to be
n plus
R
1.
n
So
plus 1.
there
So
we
there
needed
we
n
needed
plus 1
n plus 1
vectors
vectors to
to generate
to
that
generate that
polynomial as
polynomial
a r n
as a
plus 1
Rn plus
vector
1
space.
vector space.
So
So
like
simply
for
like
example,
for
let's say
example, let's say
if I have
if I have
like
like
I mean
I mean
r2,
R2,
r3,
R3,
and so on
and
up
so
to
on up
rn.
to Rn.
So
So
like
like
for this
for this
r2 vector
R2
space,
vector
I need
space, I need
two basis
two
vectors
basis
and
vectors
its
and
dimension
its
is
dimension is
2, and
2,
for
and for
r3
R3
it is 3.
it is
So
3.
like
So
this it
like
will
this
go.
it will go.
And
And
for example, if
for
I
example,
have
if I have
a vector,
a vector,
let's say
let's say
fixing n to
fixing
be
n
4,
to be 4,
then
then
if I have a
if
vector
I have a
x1,
vector
x2,
x1, x2,
x3, x4,
x3, x4,
then I can
then I can
write it as
write it
x1
as x1,
e1,
e1,
x2 e2,
x2, e2,
x3
x3,
e3
e3,
plus x4
plus x4,
e4,
e4,
where
where
e1 is
e1 is
e2 is
e2 is
e3 is
is
and E4. Sorry, this will be. So now
So
I
now
can
I
say that
can say that like
this E1,
this
E2,
E1, E2,
E3,
E3,
they are the
they are the
mm, basis vector
basis
set.
vector set.
This is
This is
basically your
basically your
basis
basis
for
for
R4,
R4.
and
And
this basis
this
vector, what
basis
they
vector, what
do,
they do,
this set
this
basically
set basically
spans
spans
R4.
R4.
So
So
that is what
that is what
I was
I was
trying to show here.
trying to show here.
This
This
basis vector
basis
set,
vector
they
set,
actually
they actually
span, they can
they
span your
can span
entire
your
vector
entire
space.
vector space.
So upon
So
taking
upon
different
taking
linear
different
combination
linear
of
combination of
uh,
uh,
these basis
these
vectors,
basis
we
vectors,
can
we can
obviously reach out
obviously
to
reach
every
out to every
part of that
part of that
vector space.
vector
Basically,
space.
we can
Basically,
explore
we
the
can
entire
explore
vector
the entire
space.
vector space.
So
So
that was the
so
idea
that
about
was the
basis
idea
and
about basis
dimensions.
and dimensions.
So
So
now the
now
important
the
thing to do
important
with
thing to
basis
do
and
with
dimensions
basis
is
and
the
dimension
linear
is the linear
independence. Like
independence. Like
we
we
can ensure
can ensure
like what kind of
what
basis
kind of
we
basis
need
we
after all.
need after all.
So
So
uh,
uh,
like if you
like
have
if you have
basis like this
basis like
B,
this B,
which is written
which is
like
written
here,
like
here,
here,
then
then
that is a
that is a
like a very,
like a very,
yeah, I mean,
I mean,
they can be
they can
like
be
called
like
as a
called as
basis
a
like
basis
this,
like this,
which I have written
which I
over
have
here,
written over here.
this 100
This 1,0,0,1
and
and
1
1, 1,
minus 1,
1 minus 1,
because
because
you would see
you would
that
see
these
that
basis
these basis
vectors
vectors
they form
they form
a linear
a linear
independence.
independence.
I mean,
I mean,
they basically
they
form a
basically
linear
form a linear
independence
independence
set.
set.
But for
But
if
for
I
if
choose a
I
basis
choose a
B,
basis B,
like
like
1020,
1020,
they cannot
they
be
cannot be
forming a
forming a
linear
linear
independence set,
independence set,
for which
for
we
which
cannot
we cannot
gender the
gender
entire
the
vector
entire
space.
vector
So
space.
we need to
So we
ensure
need to
that
ensure that
whatever the
whatever the
basis vectors
basis
that
vectors
we are
that we are
choosing,
choosing,
that should
that
be
should be
linearly independent.
linearly
Each
independent.
of
Each of
them should be
them
linearly
should be
independent.
linearly independent.
How to
And
ensure that?
how to ensure
So,
them?
like if
So
we
like if we uh,
see that, like
see
if
that, like if
B is a
B is a
basis vector set,
basis vector set,
then they are linearly
then they are
independent
linearly
only
independent only
if they satisfy
if
this
they
condition.
satisfy this condition.
So where
So where
alpha 1, alpha
alpha
2,
1, alpha 2,
all of them each
all of them
individually
each individually
goes to 0.
goes to 0.
So
So
like for example,
like for example, like in uh,
like
like
a three-dimensional
a three-dimensional
coordinate system also,
coordinate system also,
we
we
denote like three
denote like
like
three
independent unit
independent
vectors
unit
x, y,
vectors x, y,
and z,
and z.
and using this
And
unit
using
vectors we
this
can
unit vectors, we
like
can
generate entire
like generate
three-dimensional
entire
space. So
three-dimensional
that is
space.
what the
So
thing
that is what
you
the thing
can
you
see. So
can see. So
for
for uh,
this x, y,
this
z
x,
to be
y, z to be
basis vectors,
basis
they are
vectors, they
linearly
are
independent.
linearly independent.
So if they
So
are
if
not,
they are not,
then you cannot
you cannot
like label them as
like
basis,
label them as
because
basis, because
if they are like
if they
if
are
they
like
are
if
not, then let's
they
say
are
like for
not, then
example,
let's say like for example,
in this case if
in
alpha
this
3
case
is
if
not 0,
alpha 3 is not 0,
then you will see
then
that
you will see that
uh,
uh,
E3 can be written
E3
as
can
this.
be written as this.
This
This
um,
um,
E3 can be
E3 can
written
be
in terms of
written
other
in
basis
terms of
vectors
other
E1
basis
and
vectors
E2.
E1 and
So
E2.
like
So
you
like
cannot
you
generate
cannot
this
generate this
three-dimensional
three-dimensional
vector space. Like
vector
this
space.
can
Like
generate
this
a
can generate a
R3
R3
vector, but this
vector,
cannot do.
but this cannot do.
This can do
This
because
can
you
do
see this
because you
E3
see this
is
E3 is
you can
you can
write them as
write them as
in terms of
in terms of
E1 and E2.
E1 and E2.
So basically, E3 is a projects is some sort of projects are on E1 and E2, but it should not be projects on E1 and E2. If you can say that E3 should be of zero, E3 should have zero projects on E1 and E2. But in this case, E3 has some projects on E1 and E2. So for that reason, like you can say that like they are not linearly independent, hence they cannot span the entire vector space. So that's why you need to like how the basis that you are picking up should be linearly independent. So like one simple question here is um, like if you have three vectors over here and now you just have to see like whether they form a linear independent set or not. So just to do that, like as I showed you, they need to have this condition. So this condition ensures that there exists only one unique solution, because you will see that this is three vectors. Let me proceed how you can do this. Let's say I have a1 v1 plus 3v3 is 0. So that is a1 a2 and then v2 is 0. So here you will get a1 plus 2a2 0, then 2a1 so you see here, like, this forms a set of equations. So so you have to solve them like how you solve I mean a set of equations for three variables. So you will find that like in this case, like when you do, like you have to do some manipulations to do that. Like for example, first you need to like if you can call this equations as 1, 2, 3, or it's like I hope like you can solve these equations like I hope like you know how to solve equations of three unknown variables when there are three equations given, like a set of three equations. You have to solve them to get three unknown variables. So I hope you can do that. You people are familiar with it.
Yes, sir.
So once you do that, like, you will find this a1 will be minus 2a2 and this a3 will be 0. So that is the thing uh, like which you decide like whether they will be linearly independent or not, because here earlier you see, as I emphasized on this condition. So this condition like ensures a unique solution only for the case when alpha and alpha 2 all of them individual goes to 0. But here you see this a1 and a2 they are related and a3 is individually 0, and hence you can say that like for this condition there exists like many non-trivial solutions, uh, many non-trivial solutions. So this is not a unique solution problem, but many non-trivial solutions exist for this, and hence you can say they are not linearly independent. This was the unique solution condition.
Sir, please explain once again after the solution. We can find out A1, A2, yes, sir.
Yeah.
Relation
So
between two.
you will like when you
when
go
you
to
go to
like when you
when you
try to
try to
compute what
compute what
A1, A2,
A1,
and
A2,
A3
and A3
by
by
using
Yes.
these three
using these
equations,
three
like
equations, like
you will have to
you will
like
have to
subtract
like
them, you have to
subtract
add
them,
them,
you
and
have
you
to
have
add
to
them, you have to
Yeah.
find out finally.
find out
So you will
finally.
find
So you
like
will find like
A1 would be
A1 would be
equal to minus
equal to
2 A2,
minus 2
and
A2,
A3 will
and
be
A3 will
0.
be 0.
So, but
So,
as I
Yes.
but
said
as I
earlier,
said earlier,
so as I said, uh, your condition
your
is this:
condition is this:
alpha E1
alpha
plus
E1
alpha
plus
E2
alpha
to
E2
alpha
into alpha
n alpha
n
and En
alpha and En
will be 0
will be 0
only if
only if
alpha 1, alpha
alpha 1,
2,
alpha 2,
and all
and
other
all
alpha
other
n,
alpha n,
each individual
each
goes to
individual goes
0.
to 0.
Zero.
But here
But
you
here
see
you see
this A1 is
A1
this
is
A1 is basically those
A1 is
alpha
basically those
which I have
alphas
written there.
which I have
So for
written there.
in this
So
question,
for
Mm.
in this question, this
A1 is
A1
equals to
is
minus 2
equals to minus 2
and
A2,
A3 is
and
0.
A3
Mm.
is 0.
A3 only
So
individual
A3
goes to
only
0,
individual
the
goes to 0,
other
but
is
the
not.
other is not.
So
So
No.
that like you
for that, like you will
uh,
see,
in for
like
this kind of
for
situation,
this kind of
you will find
situation,
that
you
your
will find
system
that your system of
this
equation,
system of
this
equation
system of
doesn't
equation
have a unique
doesn't have
solution.
unique solution.
Mm.
So if they doesn't
So
have
if
unique
they doesn't
solution,
have unique solution,
that means
that
these are
means
not linearly
these are
independent.
not linearly independent.
A1, A2.
Mm.
A1,
So
A2, A3.
that is why
So
this
that is why
basis
this
which we
basis
have
which we have
chosen here, they are
chosen
not
here, they are
linearly
not
independent.
linearly independent.
So
So
So here, if we get all the values equal to 0, then we
yeah,
will call it as
yeah.
linearly
V1,
Then
V2,
independent.
V1,
V3
V2, V3
would be
would be
your
your
like basis.
like
You can
basis.
call
You
that
can
as
call
your
that as your
basis vector.
basis
And
vectors, and
using these three
using these
vectors, you
three
can
vectors, you can
construct
construct
R3 vector
R3
space.
vector space.
Mm. Okay.
Okay. So
So
so based on this, like I wanted to have another question.
another question.
So maybe
So maybe
like I can just
I
write
can
that
just
question
write that
here.
question here.
Maybe you can
Maybe you can
like
like
individually you can try
individually you
it
can try
yourself
it
and we
yourself,
can
and
discuss
we
it
can
like
discuss it
next week.
like
So
next week.
just
So
adding
just
to this question,
adding to this question,
um,
um,
let's say
let's say
let's say find a vector
find a vector
v2 prime
v2 prime
such that
such that
v1
v1
v2 prime
prime
and v3
and v3
are
are
linearly dependent or
dependent or
independent
independent
respectively,
respectively,
and so
and
explicit
so explicitly
that they have this
that
property.
they have this property.
So the thing is
So
like you
the
have to
thing is, like you have to
pick a new
pick a new
v2, that is
v2,
v2
that
prime,
is v2 prime,
such that like you
such
have to
that
check it
like you
whether
have to
like
check it
that
whether
will
like
be
that will be
linearly independent or
linearly independent or
dependent,
dependent,
and
and
you have to solve that
you have
like
to
how
solve that
you are
like
proving
how
them.
you are proving them.
So like you can
So like
arbitrarily
you can arbitrarily
pick something
pick
v2 prime
something
to be
v2 prime to be
something x y
something x,
z,
y, z,
and then you can
and then you
proceed ahead.
can
Like
proceed ahead. Like
so give
so
it a try.
so
Like
give it a try.
how you
Like
can
how you can
prove them
prove
like
them
linearly
like
independent,
linearly
or what
independent,
would the case
or
if
what
they
would
are
the
not.
case if they are not.
So so
So
then
so then
like so the,
so the,
um yeah,
yeah.
maybe we can
So maybe we can
discuss more on this
discuss more on this
next week. So
next week. So
What about V1 and V3?
v1 v3
They are
V1
also
V3
vectors.
v1 v3 you have to
V1
take
V3
them
you have to
same
take them
what
same
you took.
what you took.
So sorry, once again.
v1 v3
V1 V3
v1 v3
leave
as it
V1
is.
V3 as it is.
Okay.
But
But
you instead of v2
you instead of
you
V2
define a new
you
v2
define a new
that
V2,
is xyz,
that is
Okay.
and you have
XYZ,
to
and you have
find
to
what this
find
xyz
what
is,
this
so
XYZ
that
is,
like they would
so
be
that
Okay.
linearly
like they would be
independent or
linearly
dependent.
independent or
So you have
dependent.
to
So you have to like
follow this
follow
idea here.
this idea here.
like where like you will find that
you
in
will
that
find
case
that
A1,
in that
A2,
case
A3,
A1, A2,
each
A3,
individually goes to
each individually goes to 0.
Yes, sir. But
okay.
Okay,
We can move on.
we
So
can
before
move
moving on,
on.
like
So
if there
before moving
any
on, like if there
question, like
any
they can
question, like they
go
can
on,
go on, they
they can
can
ask
go,
like
they can ask like,
So can I ask one question from
yeah,
the
yeah,
course
yeah,
lecture?
yeah,
yeah, yeah.
yeah, yeah.
In the Cauchy-Squarce inequality for the Euclidean vectors,
Uh-huh.
um, the instructor told us that for A and B, for the sum to be minimum, we have to make A parallel to B. So, I wanted to ask that why is it such that we have to make A parallel to alpha B to make them parallel, to make the sum minimum?
Sorry,
Sorry,
you're telling like
you are telling like
what are A and
what are
alphas?
A
Like I
and
couldn't get.
alphas, like I couldn't get.
Like in Cauchy-Squarce
Huh.
inequality, we have two vectors, alpha B and A,
Alpha B.
Alpha
and
B.
alpha times B,
Okay.
alpha is a
Okay.
scaling factor, and
Uh,
A.
Okay.
And so we
okay.
have to make the sum which is C minimum.
Yeah, yeah.
Yeah,
You have
yeah.
to prove
You
that like
have to prove that like
third side is
third
minimum.
side is the minimum.
Yeah, so we have taken an assumption
Uh-huh.
that the shortest vector must be such that it is perpendicular to B, which means that the sum which is C should be perpendicular to the vector B.
Okay.
Okay.
So like why are we taking this assumption?
Uh, so
Uh, so
the idea would be
the
there,
idea would be there. I mean,
like,
like,
uh, do you have any
do you have any
like I mean
like I mean uh,
that
uh,
proof the
that
idea like
proof the idea? Like,
said that in
can you
the
say that
chat
in the
message like
chat message?
actually I'm not
Actually, I'm not
following
like
that
really
properly,
following that
like as you
properly.
said, like
Like, as you
the,
said, like
the methodology which you
the
said.
methodology which you said.
Oh yes, 1 minute I will type it.
Okay.
Okay.
Okay, if there's
Okay.
any
If
more
there's
question,
any more question, like,
okay,
okay,
C
C
equal to A
equals
plus
to A plus
alpha B.
alpha B.
You take C.
C.
Well,
Well,
here actually
here
I'm
actually
not able
I'm
to
not able to like
follow this,
follow this,
like
like
what
what
sir was
sir was
explaining
explaining
exactly. I mean,
exactly. I mean, what
what he
what
basically
he basically
meant to be
meant to
like side
be like
lens
sidelines,
or
I mean, like after writing that assumption, he took the dot product of C and B and put it equal to 0.
maybe
or
like
maybe
what
like
I can do,
what I
maybe
can
I
do,
can
maybe I can
look that
look that
a lecture. So
lecture.
do you
So do
remember
you
which
remember
lecture it
which
is? Like,
lecture it is? Like,
Yes, 1 minute.
uh,
It's the Cauchy-Squarce inequality for Euclidean vectors.
so
the first
the
lecture of
first
that
lecture of that
Cauchy-Schwarz
Cauchy Schwarz
inequality.
inequality.
The first.
Yes.
First one.
Okay, so
Okay, so
I will look
I
onto
will
that,
look onto
and
that,
then
and then
what you can do,
what you
maybe
can do, maybe you can like
you
you
can
can
drop
just
the
drop
same
the
question
same
there in
question
the
there in the
discussion forum. I
discussion
think
forum.
there
I
is a
think there is
discussion
a
forum
discussion
where
forum
you can
where
ask
you can ask
questions.
questions.
Okay, sir.
So you can
So you
drop the
can
same
drop the
questions.
same
I
questions.
will I will
I
surely
will
reply
surely
to you
reply
after
to you after
looking at that
looking at that
video very well.
video
Set
very
you,
well.
no
Set you,
problem.
no problem.
Okay, so thank you.
Okay,
Okay.
so
So
you can
you
do
can
that. I
do
can
that.
see you
I
there.
can see you there.
Okay.
So
So
anything else?
anything else, like,
If there's anything
if
else,
there's anything else, like
any more doubts,
any more
questions,
doubts or
or any
questions
comments
or
also.
any comments also.
If not, then like
If
we
not,
can
then like
move
we
on.
can move on.
So
So
this is
this
the
is
next thing
the
is
next
your
thing your
is inner product.
is inner product.
So for
So
inner product, I think
for inner
again,
product, I think again,
so you must be aware
so you must be aware,
like from your
like
lectures,
from your lectures.
uh, inner product are the the important like I mean your your important like feature of this vector spaces. So basically like you would find in various other places, that may be physics or any other uh, courses also. Like using inner products, there will be various physical things can be explained. So here to solve some courses, again I have put up some few properties here. So the basic few properties of inner product is like they obey this symmetric condition. Then they they have this linearity property, associativity, and then again this positive definiteness. That is one of the important feature of this inner products. So they are basically positive definiteness. So I think this would all have been explained to you well by Professor Aditya Sharma. So I hope like all of you like gone through those lectures. So has everyone gone through those lectures?
Yes, sir.
Okay. So because this question would be only helpful like if you would have followed those lectures. So
Yes, sir. All not completed, sir.
so you have not completed. So I mean you have started like going through the lectures, but not the whole of them, right?
Yeah, not
Okay,
completed.
okay.
Just started.
Oh, started. Okay. So like I would say like just go through them. Like first you have to go through those lectures. You have to follow them properly, and then you can at the same time you can also work on the assignment which is already out. And meanwhile, like uh, like to further like to understand more in a different perspective, you pick different problems. So like these problems which I am picking up here, like they would like give you a new perspective to understanding. Like probably like the same thing would be, but just like we are basically going into some specific details. So that would may clarify some of your basics and some other doubts that would be like causing problem with you and understanding the things. So so that was the idea of this problem solving sessions. So yeah. So the next thing is like
So you are from which institute, sir?
I'm from IIT Kanpur.
IT Kanpur. Physics department, sir?
Right.
Okay. Thank you, sir.
Okay. Like, do you have any like any like what was that inquiry about?
I wanted to know your institution,
Oh,
sir.
okay, fine.
Like this course is under IIT, means different,
Okay,
means people are from different institutes. So I just want to
okay,
know.
fine. So yeah, the next question is like so if so V is a vector space of continuous and continuous real function defined on an interval. We are calling that I, which belongs to this R, and then we are telling that there is a function or there is operation, let's say f, which like takes I to R. I mean that resultant also belongs to this R. So the rules are like this: if you have f g functions or operations uh, like belonging to this v, then f plus g will take you to R. So that is uh, x is basically mapped to f plus gx in this way, f of x plus gx. So this is again like the one which we were doing for polynomials. So these two are basically the two closure conditions. That is all like I was trying to like show you before. So like here what the thing is like if they closer like they need to have this closer condition in order to be a vector space. Uh, so but here the thing is like so that the following map, this mapping defines an inner product space,
inner product space,
inner product on
inner
B
product
actually.
on B
Uh,
actually.
so they
So
basically
they basically
this definition
this
is a
definition
inner
is
product
a
on
inner
vector space
product
V.
on
So
vector
that is
space
what
V. So
we
that
want
is what
to show
we
here.
want to show here.
So
So
so like as I told, like
as
for
I
a inner
told, like
product,
for a inner product,
you need to have
you need to have
these conditions.
these
You
conditions.
need to
You need to
do
be
these
looking
conditions,
into these
whether
conditions,
they are
whether
satisfying
they
or
are
not.
satisfying
So
or not.
you have to check
So
them whether
you have to
they
check
hold.
them whether they hold or not.
So
So
so the first one, like
so the
to
first
check
one, like
the
to check
symmetric
the symmetric
condition.
condition.
For symmetric,
Symmetric.
so
So this
integral is basically on
integral is
I.
basically on
I, which I can just simply
which I can
write.
just simply write.
That is
That is
GF.
GF.
So that is
So that
proves your symmetric
proves your
property.
symmetric
And
property.
for
And
uh,
for uh,
linearity,
linearity,
like for linearity,
like for linearity,
you can
you
say
can say
This integral form is given in the course, or it is like given in the question.
sorry.
Like I didn't find it in the content of course, the integral form.
Sorry,
sorry,
could you repeat your question
could
again?
you repeat your question again?
I mean this integral
Uh-huh.
form that f
Uh-huh.
comma g equals to integration of dx if
Uh-huh.
x dx.
Uh-huh.
Like this was not given in the content
Oh,
when they are teaching.
okay.
Okay.
Well,
Well,
uh, y-
uh,
yeah,
yeah,
you may not have
you
found
may not
this
have
anywhere, but
found this
this is
anywhere, but
like
this
I'm
is
not like
like I'm
solving
not
any
like
integral here.
solving any
I'm just
integral here.
telling this
I'm
is the
just telling this is the
definition of inner product
definition of
in
inner
terms of
product
functions. So
in terms
this
of
basically
functions. So this
represents
basically
the overlap
represents the
integral.
overlap integral.
So
Okay.
So
this inner products,
these inner
when
products,
you
when you
talk about in terms of
talk
functions,
about in terms of
basically
functions,
here you see
basically here you
f
see
and g,
this
they
f
are
and
basically
g, they are basically
functions.
functions.
Like these
Like
functions,
these
like in
functions,
order to
like
define
in order to
inner
define
product
inner
among
product
them, you
among them,
calculate an
you
integral like
calculate
this.
an integral like
So
this.
this integral,
So
what
this
actually
integral,
it
what
calculates,
actually it calculates,
it is a like we
it is
call
a
this
like
integral
we
as
call this
overlap integral,
integral as overlap
because it
integral,
calculates
because it
how much of
calculates how much of
function f and
function
g
f and
they
g
contribute
they
together.
contribute together.
Like there would
Like
you find
there
that
would
function
you find that function
like this, some,
like this,
let's say
some,
f
let's
is
say
some
f is some
uh, like some
like some
some
like
sine
some
function, and
sine
then
function,
you
and
would
then
have
you would
g
have
would be some
g would be some
cosine function, and you
cosine
would find
function,
some
and you would find
like
some like
overlap region among
overlap
them.
region
So
among them.
that
So
actually
that actually
gives you the
gives you the
overlap integral when you
overlap integral
do
when you
this
do this
do this integral. So
do
that is
this
the
integral.
definition
So
of
that is the
inner
definition
product
of
in
inner product in
context of
context
functions.
of functions.
So
Okay.
like
Thank
this is
Like
just a
this is
definition.
just a
I'm not
definition.
talking about
I'm not talking about
explicitly something about
explicitly something about
integrals or something.
integrals or
So
something.
like
So
I'm just
like
trying to show
just
you like
trying
how
to show you like
this
how
inner product
this inner product
like can be
like can be
proved using these
using
definitions. I mean,
this definition. I mean,
if
if
I have to prove this
I have to
integral to
prove
be
this
an inner
integral to
product,
be an inner product,
then they must satisfy
then
these
they must
conditions.
satisfy these conditions.
Okay. Thank you.
Mm. So
So
yeah.
yeah.
So as I
So
showed
as
you
I showed you
how they can be
how they can be
symmetric here in
symmetric
this
here in this
first part, and so the
first
second
part,
is
and
like
so the
the
second is like the
linearity condition.
linearity condition.
So the linearity
So the
condition was
linearity
this:
condition was this:
when you have
when you
alpha
have
u
alpha u
and w,
and
they are
w, they
like
are
we are taking the inner
like we are
product of
taking
alpha
the
u
inner
and
product of
w.
alpha u
They
and
can
w.
pretend as
They can pretend
alpha
as
of inner
alpha of
product of u and
inner
w.
product of u and w.
So That is what I'm doing
that
here.
is what I'm
So
doing
I'm
here.
taking here
So I'm
lambda, or
taking here lambda, or
let's stick to
let's
alpha.
stick to alpha.
So
So
alpha f plus
alpha
gh,
f plus g
I can
h.
write this as
I can write
alpha
this
f
as
of x
alpha
plus
f
g
of
of
x
h
plus g of x
times h of x
times
according
h
to
of
this
x according to this
integral definition.
integral definition.
So
So
that would
that would uh,
so that would, like,
so
I can
that would,
write this
like, I
further.
can write this further.
And that is basically
That is basically
LFH
FH
plus GH.
GH.
Or sorry,
Sorry,
again I'm like
again I'm
writing lambda this.
writing lambda this.
So
So
this is your
this is your
like, the thing is like,
like, the thing is like,
I have
here I have
combinedly proved
combinedly proved
3.
2 and 3.
So
So
you can individually
you
solve them,
can
or you
individually
can
solve them,
solve
or
them
you can
together. So
solve
that
them
is what you
together.
can
So
see:
that is what you can see:
linearity and
linearity and
associativity.
associativity.
So
So
like, the
like,
first thing in
the first
linearity
thing
you
in
see this
linearity, you see
alpha,
this
which was multiplied
alpha,
with
which was
q,
multiplied with q,
and then we are taking the
then we are
product of
taking
alpha
the inner
unit
product of
w,
alpha unit
that gave
w,
this thing.
that gave
So
this thing.
that is what
So
this
that is
part
what
does.
this part
So
does.
initially I have,
So
let's say,
initially I have, let's say,
alpha f
alpha
and h,
f and h,
and that gave me
that gave me
alpha
alpha
fh. So
fh.
this is, which
So
is this
this is,
part.
which is this
And the
part. And
second
the
part is this
second part is this
associativity. So that is
associativity.
also,
So that is also
I have shown with
I
in
have
the
shown
same,
with in the same
like,
like
in the same
in
exercise.
the same
So that
exercise.
is
So that is
this thing.
this thing.
So just don't get
So just
confused. Like, you
don't get
can
confused. Like, you can
see them
see
individually
them
also.
individually also.
And then the
And
final
then
thing
the
is
final thing is
the
the
semi-positive
semi
definiteness.
positive
So
definiteness. So maybe
again, I need a bit
I
space.
need a bit space here.
So
So
Sir, excuse me.
uh
Sir, what about alpha in the second part? Sir, with sorry, lambda with the second part, G.
uh,
Lambda is multiplied with fx plus gx, sir.
okay, just a
okay,
minute, like,
just a
let
minute.
me,
Like, let me.
Second part of the
yeah, sure.
Yeah, yeah.
answer.
I'm just finding
I'm
a
just
space,
finding
like,
a
I'm not
space here. Like, I'm not
getting it right here.
getting it right here.
Just give
Just
me,
give me a second.
yeah.
Yeah.
So
So
yeah, you were asking
yeah,
like
you were
alpha
asking like alpha
was multiplied with
was multiplied with
this f.
this f.
Uh, could you repeat it again?
Could you repeat it again? Like,
Yes, sir. Alpha was multiplied with fx,
Uh,
then also with gx also. So what about the alpha in the second part, sir?
no. That
no,
In the answer
that
with
alpha was multiplied
alpha
with
was
only f.
multiplied with only f.
f.
Only f.
Oh,
So what?
okay, okay.
What I did,
So
I
what I
first
did,
proved,
I
like, you
first
can
proved,
also,
like, you
if
can
you're having
also,
confusion,
if you're
you
having
just first
confusion,
take
you just
alpha f
first take alpha
and
f
h,
and
and
h, and
you
Yeah.
prove them
you
this
prove
Yes.
them
alpha
this to be
fh.
alpha
And the
fh.
second is like,
The
Alpha
second is like,
you take
you take
alpha f
alpha f
plus g
plus g
and G. Okay,
h,
okay, sir.
h,
and
and
then you prove
then you
this
prove
as
this as
alpha f
alpha f
uh,
uh,
h
h
plus g h.
g
So
h.
this is your
So this is your
linearity property,
linearity property,
and this is your
and this is
associativity.
your associativity.
So this is your
So this
associativity.
is your
So
associativity. So
I just
I
clubbed
just
them together. I
clubbed them
combined and
together. I
stored you in
combined and stored
here.
you in here.
So
So
this was your third
this was your
property.
third property.
So I hope it is clear to you.
it is clear to you.
No, yes, got it,
Okay.
sir. But
Okay.
So then, for semi-positive definiteness, like
Semi-positive
you have to
definiteness,
show
like you have to
this
show this
f and f,
f and f,
that is
that is
f square x.
square x. So
Here you can see.
here you can
So
see. So
the integral
the integral
uh, will be greater
will be greater
greater
than or equal to
so it will
zero.
be
So it
zero
will be
if
zero
f is
if
a
f is a
zero function.
zero function.
So if f is
So
zero,
if f is
then
zero,
you will get this
then you will get this integral to
zero
be
function.
zero function.
Otherwise, since
Otherwise,
as
since
I
as I
showed you here,
showed you here,
um,
um,
this
this
uh,
uh,
like where it was
it was
like
like
here this integrand
here this integrand is on
uh,
like
the integrand is
the integrand is basically like
uh, greater than or equal to
greater than or
this
equal to zero on
interval
this interval
I.
I.
So you can say
So you can say that like
this integral
this integral
that the whole
that the whole uh,
when you do this
when you
integral,
do this
like when you
integral, like when you
do
uh,
this integral over
do
I,
this integral over I,
you will get this to be
you will get
positive.
this to be positive.
So that
So
itself
that
ensures
itself
that
ensures
this
that this um,
semi-positive definiteness
semi-positive definiteness
feature.
feature.
So
So
that defines your
that defines your
like how inner
like
product
how inner product
can be
can be
can have the
can
structure.
have the
So like
structure. So
as
like
I showed you
as I
these
showed you like
properties,
these properties, each
after
of them
they
after when they
satisfy for
like satisfy for
uh,
this
n- definition
new
of
definition of
inner product,
inner product,
like they
like they
like
like
I have this
I have this
FG
fg
as an inner product
as
which
the
I'm
inner
defining
product
in
which I'm
terms of an
defining in terms
integral,
of a
which is
integral,
right
which
this
is
one.
right this one.
So if I am
So
claiming
if I am claiming this to be
inner
an
product, then
inner product,
I have
then
to
I have to
check individually
check
each
individually
of these
each of these
are like
are like
being satisfied
being satisfied
for my
uh, for my
function f and g.
function
If
f and g.
they are doing so,
If
then
they are doing
they
so,
can
they
then
can
this
then
definition of
this definition of inner
is
product
valid.
like is valid.
So that is what the
So
purpose
that
of
is
this
what the purpose of
question.
this
So
question.
like if there's
So like
anything
if there is
doubt,
anything
like they can
any doubt, like they
speak up.
can speak up.
Then we have the
We have the
like the last section.
the last section.
So it was
So
mindful.
it was fine for
If there's any question,
if there's
they
any
can speak,
question,
or
they
we
can
can just
speak, or we can just
wrap up the things
wrap up
with
the
the
things with the
last discussion
last
on
discussion
orthonormality.
on orthonormality.
If not, then
If not, then
I can.
I can.
So
So
so we can move on
so
to
we
this
can move on
orthonormality,
to
the
this
last section.
orthonormality, the
So
last section.
orthonormality,
So
like again,
orthonormality, like again,
you would know, like
you would
so
know,
from
like
inner
so
products,
from
we
inner
can
products, we can
define orthonormal
define
basis
orthonormal basis
for a vector
for
spaces.
a vector
Like
spaces.
for a
Like
given vector
for a
space,
given vector
like
space, like
you obviously
you
would have
obviously would have
already got an idea
already got an idea
from this
from
discussion, like
this
which we
discussion
have been doing so
which we
far.
have been doing
The
so far.
basis that we
The
have been
basis
talking
that
about
we were
in
talking about
earlier
in
questions,
earlier
they do
questions,
obey
they do obey
a sort of
a sort of
orthonormal conditions among
orthonormal
them.
conditions among
So
them. So
that is like
that
basically
is like basically
this
this
condition.
condition.
So
So
so you
so you
ensure
need
that
to ensure that
the vector spaces
the
that
vector spaces
you
that
are
you are
working on,
working on,
the basis that
the basis that
chosen,
you have
they
chosen,
should have
like they should
orthonormal
form an
basis.
orthonormal basis.
So
So
like having an
like
orthonormal
having an
basis,
orthonormal basis,
that
that
will
like that will
independently
independently
ensure that
like ensure that
they are
they are
like linearly independent
linearly independent set of
vectors that you have
vectors that
taken
you have
to
taken
construct your
to
vector space,
construct your vector
or
space,
like you can
or like you can
work on those
work
vector,
on
on those
those
basis
on
vectors
those basis
to
vectors
like
to
uh,
like
to
to
understand like various
understand like
other
various other
like
like
transformations
transformations
other
or other
properties that
properties
other
that
features that
or
you
other
can do with
features that
vector
you can do
spaces.
with vector
Like
spaces.
so having
Like so
orthogonal
having
basis is very
orthonormal
important,
basis is very important,
so that like it
so that
can
like
form
it can form
a sort of
a sort of
reference uh,
reference uh,
for you
for you,
that particular
that particular
orthogonal basis can
orthonormal
help
basis
you
can help you
like do
like
various other
do various
transformations
other
on that
transformations
vector space.
on that vector space.
So
So
if you would
if you
arbitrarily
would
go with any
arbitrarily
other
go
vector
with
space,
any other vector
then
space,
they may not
then
satisfy
they may
linear
not satisfy
independence, and
linear
there can
independence, and
be
there can
other
be
consequences.
other
So,
consequences.
so then
So then
the the last question is this:
last
like,
question is this:
if
like,
uh,
if
if you have this
if you have this
E1 and E2
E1 and
vectors,
E2 vectors,
then
then
uh,
uh,
then will they
then
satisfy?
will they satisfy?
Will they form
Will they
orthogonal
form
basis for
orthonormal
R2?
basis for
You
R2?
have to
You
check.
have to check.
And
And
then there is the other
then
part.
there is
So
the other
first
part.
part is like,
So first part
so
is
these
like,
vectors
so these vectors
form an
form
orthonormal
an
basis
orthonormal basis
for R2.
for R2.
So
So
to
like to
to begin this,
to
we
begin
can
this, like we
just
can just
for this, like you have to
for
only
this, like you
assume
have to only
this
assume
condition
this
right here.
condition right here.
So
So
for that, you
for
just need
that, you
to
just need to
check this
check this
E1.
E1.
First condition
First
is
condition is that
this
this
should give you
should give
1.
you 1.
So
So
here you can
here
see
you can
that like
see that like
uh, when
when
I hope like
so I hope
you
like
know how to take
you
inner
know how to
products.
take inner products.
Let me
Let me
I can show you.
maybe I can show you.
So
So
oh, this is one.
this is one.
So
So
you know
so you
take
know
inner
how
products.
to take inner products, no?
So then
So then
E2,
E2 E2,
you will find that this will
you will
also
find
give
that
you
this
one.
will also give
So
you 1.
hence
So
you
hence
can say
you can say
this E1
this E1
EJ,
EJ,
they obey this
they
condition.
obey this condition.
So this when
So this when
I
I
so this delta is a
this delta is
0,
zero,
is not equal to.
I is not equal to 0.
So
So,
so are you getting like
so are you
what I
getting
just
like
did? So
what I just
just
did?
simply
So just
took
simply
the inner product.
I took the inner product.
So everyone is
So
familiar with inner
everyone is
product,
familiar
how
with
they
inner
are
product, no? How they are
like how we
like
compute
how
inner
we
product.
compute inner products.
So the
So the
next part was
next part was like
express a vector
express a vector
W
W
in this form
in this
by
form
computing its
by computing its
components WI
components
with respect
Wi with respect
to this basis
to this
EN
basis EN
through projection
through
onto the
projection
basis
onto
vectors.
the basis
So
vectors.
like
So
now
like
the task
now
is like
the
you
task
have to
is like
construct
you
this
have to
W
construct this
vector
W
minus
vector
2 3
minus 2 3
such that like
such that
you
like
have to take
you
the
have
help of
to
this
take the
basis
help of
vectors.
these basis
So
vectors.
I mean
So I mean
it is basically you
it
need
is
to
basically you need to
calculate
calculate
these two things.
these two things.
First, like it
First,
has
like it has
this W has
this
two
W has
components.
two components.
So let's say
So
W1,
let's say W1,
and that has
that has
you need to
you
calculate
need to calculate
E1
E1
W,
W,
and for W2
and for
you need
W2
to calculate
you need
E2
to calculate E2
W. why you need to do
why
this
you need to do
inner
this
product of
inner product
E1W,
of
because
E1W,
here
because
it is said
here
to
it
you,
is
you
said
have
to
to
you, you have
get
to
this components
get this
W and W2
components W and
through
W2
projection onto
through
the basis
projection
vectors.
onto the basis
So for
vectors.
W1,
So for W1,
you
like
you
you
can just
you can just
project this W vector
project this
on
W vector
E1,
on E1,
on this basis vector
on this
E1,
basis vector
you
E1
get
to
W1
get
component,
W1
and this
component,
W,
and
and
this
for
W,
W2 you can
and for
do the same
W2 you can do the
along
same
E2,
along
that is
E2, that is
taking projection of W on
taking
E2.
projection of W on E2.
So
So
are you people getting know
are you people getting know
what
like
I'm trying to say?
what I'm trying to say?
Hello, like,
Hello,
are you there?
like, are you there?
Hello.
Hello.
Yes, sir. They are trying to understand, sir.
Okay, are you getting?
Okay, are you
If
getting
there's
know?
any problem, you
If
can
there is any problem, you can speak up.
like. Are you able to follow now? Like,
Are you able to follow
Sir,
now? Like,
yeah, yeah, sir. Please continue.
okay.
okay.
So for
So for
W1,
W1,
so
so
as I said, like you
as
have
I
to just
said,
take
like you
inner
have to
product
just
of
take
these two.
inner product of these
So
two.
E1,
So
so
E1,
E1, like
so
we have
E1,
E1
like we
as
have E1 as
this 1 by
this
root 2
1
1.
by root 2
So that
1
is
1. So that is
1 1, and
and
inner product with
inner
W.
product with
So
W. So
W is
W is
minus 2 3.
minus 2 3.
This is W.
This is W.
So the
So the yeah.
so that will
So that
give
will
you
give you
minus 2
minus
plus
2
3, that
plus
is
3, that is
1 by
1
root
by
2,
root 2,
and
and
then
then
yeah,
yeah,
W2
W2
is 1 by
is
root
1
2.
by root 2.
Your E2 is
Your E2 is
1, sorry,
1, sorry,
1 minus 1.
1
I think
minus 1.
this will
I
be
think this will be
root 2.
root 2,
1 minus 1.
1 minus 1.
Then
Then
W is minus 2 3.
W is minus 2, 3.
That will give you
That will give you
minus 2 minus 3,
minus 2
that is
minus 3,
minus
that is
5
minus 5
by root 2.
by root 2.
So that is how
So
you
that is
construct your
how you
W
construct your W
along
along
this basis
this
vectors. So
basis vectors. So
uh, so your
so
W
your
is
W is
1 by root
1 by root 2
E1
E1
plus
plus
or minus E2. So that is your
so
W.
that is your W.
So
So
Yes.
yeah,
so yeah,
this is like
this is like
using orthonormative.
using
Like you
orthonormative.
can
Like you can
construct like
construct
how
how
here you can say
here you can
that
say
like we
that
found
like
that
we
E1
found that
E2 form
E1 E2
orthonormal
form a orthonormal
basis. So using
basis.
that
So
orthonormal
using
basis,
that orthonormal basis, like
we
we
found like how
found
we
like
can
how we
like
can
obtain
like obtain
components of any other
components of
arbitrary
any
vector,
other
that is
arbitrary
W.
vector, that is W.
So
So
orthonormality is very
orthonormality is very
important element
important
of this
element
vector
of
spaces,
this vector
which
spaces,
directly follows
which
from
directly follows
products.
from inner
So
products. So
that is the thing.
that is the thing.
Yeah. So if there
Yeah.
is
So if there
questions,
is
like
any questions, like
they can ask
they can ask
like anything that you
like anything that you
didn't find
didn't find
that
uh,
went
that
good
went
here or
good
something.
here, or
If you had
something.
issues
If you had issues, like
anything, like you can tell
anything, like
also
you can
this
tell
week's
also this
course.
week's
Like there was
course. Like
one question
there was one
from
question
a
from
person like
a person, like
on this coaches
on
words
this coach's words
inequality lecture video.
inequality
So
lecture video. So I will
and
look
also
onto that, and
try
also I will
to
try to
let you know
like let you know
in the discussion forum.
in the discussion forum.
So so
So
apart from
so
that, if there's
apart
some
from
more
that, if there's some
questions or
more
doubts,
questions
anything
or
related
doubts,
to this
anything
week,
related to this week,
or also something
or
in
also
general,
something in general,
they can tell.
they can tell.
Yeah.
Yeah.
Was everything fine?
Was everything fine?
Or
Like, or
like someone
someone
like
like
at least
at least
tell me like if
tell me
it
like if
was all
it
right
was
with you,
all
or
right with you,
if
or
not, like
if
we can
not,
do
like
something
we can do
specific
something
more, or we
specific
can
more, or you can
change
change
our
our
discussion in some
discussion in
a
some
bit a different way,
bit
or
a
like
different way, or
anything
like anything
you have any
you
comments
have any
to add,
comments
or
to add, or
any difficulties,
any
any issues, any
difficulties, any
doubts.
issues, any doubts.
Everything was fine.
Everything was fine.
I think like
I think like
Yes, sir. Yes, sir.
I think
Things are
I think
fine.
except you, no
Yeah.
one
except you,
is
no
there in
one
the
else
meeting
is there in the meeting
to be there.
I
to be there.
don't know, sir.
Okay, so
Okay, so
I see some
I
names
see
here,
some
but
names here, but
maybe
maybe
they would have
they
just
would
left
have
the
just
meeting
left the
while
meeting
making
while
Yes,
making
they have
making the
left
mid
making the
actually.
mid
joint.
joint.
But
But
Actually, sir, means I have my own homeworks. I have to do complete it. I have not yet completed. I'm going through it.
okay,
So, in due course, when I will come up with some difficulties or doubts, I will discuss in the next
sure.
session. That is why I
sure.
asked you are from which institute or not, so that I can connect with you.
Sure, sure.
Oh,
If
sure,
there's
sure.
something
If
very
there's
specific
something
question,
very specific question,
like
like
if you're not getting
you
like
if you're not getting like
for ease of
for
communication,
ease of
like you can
communication,
also
like you can also
mail me on
mail
this
me on this
email. Like I'm
email.
writing
Like
down my
I'm writing
email right
down
here.
my email right here.
So
Okay, sir, I'll
So
note it down.
so you can
so you can
mail me here
mail me here
if there's
if there's
any particular
any
doubts, or
particular doubts
you are
that
unable
you are
to,
unable
like,
to
because
like,
in
because
discussion forum
in
also, like
discussion
if
forum also, like if
maybe
maybe
I may not like
I may not like
instantly able to like
instantly able
check
to
your
like
questions and
check your questions and
reply to them. So
reply to
maybe
them.
email
So
could be
maybe
better.
email could be
Just
better.
for ease
Just
of
for
communication, you
ease
can
of communication,
try
you
it
can
here,
try
in
it
this
here,
email, or you
in
can
this
also
email, or you can also
drop your question
drop
in
your question
discussion
in
forums. So there
discussion
also I
forums.
will
So
see,
there also I will
sort
see,
out any issue if
sort
there
out
is.
any issue if there
Uh,
is. Uh,
Sir, this 23, sir, ARYABRATM
yeah,
23.
yeah,
at
2 3 at
I
Okay,
iitk.ac.in.
iitk.ac.in.
okay, sir.
Yeah. So
So
yeah, and also that
yeah, and
there's
also that
some
there's
people they've
some people
also
they've also
told that
told
like
that that
this was fine
this was
with them,
fine with
like
them.
this
Like this
session was fine.
session was like
Ridhini
Ridhini
said it was
said
fine,
it was fine,
and
and
Nachiketa is
Nachiketa
also
is also
fine with
fine
this
with this
session. Like
session. Like
okay,
okay,
so if
so if
everything is
everything is
fine, like,
fine, like,
or if
or
there's
if
something
there's
that
something that
was troubling
was
you, like
troubling you, like you can
like
like uh,
you can
you
share
can
that to me
share
maybe
that to
next
me
week. Also,
next
you
week.
can
Also, you can
communicate by email, or
communicate by email,
through discussion forum. Like
through
we
discussion
can
forum. Like
check
we
there, we can
can
try to
check there.
sort
We
out
can try to
any
sort out
doubts.
any doubts.
So in the meantime, like
So in the meantime, like
just
so just
so stay
so
tuned with those
stay tuned with
lectures.
those lectures. Like you
And you need to like
and you need to like
cover those lectures
cover
properly,
those
so that
lectures
once
properly, so
you
that once
are
you are
able to follow those
able
lectures
to follow
properly,
those
then
lectures
it
properly,
would be
then
more or less
it
like
would be
you
more or
can
less like
do
you
those
can do
assignments,
those
but still
assignments, but
there can
still
be some
there can
prevailing
be some
issues
prevailing issues
in particular
in
parts or
particular
sections of
parts or
the
sections of the
topic,
topic,
or
or
the subject matter
the subject matter
that has been
that has been
like delivered to you.
like
Like,
delivered to
I
you.
think
Like I think
it is more or less
it is
completely
more or less completely
like delivered in a
like delivered in a
proper explanation in a
proper
detailed
explanation
fashion.
in a detailed
So,
fashion.
but still,
So, but
there can
still,
be
there
some
can be
minor doubts, or
some
could be
minor doubts, or
some
could be
like
some
primary
like
doubts as well,
primary doubts as well.
which we
So,
can
which we
share it
can
in live
share it
interaction
in
like
live
this.
interaction
So
like
we
this.
can
So we
like
can do that.
maybe
Like
in coming
maybe
week
in coming
onwards, like we
week
will
onwards,
also
like we will
discuss
also
some
discuss some
assignments problem also.
assignments problem also.
So until
So
then, like if
until
there's
then,
no
like if there's no
questions or anything
questions
from
or
your side, then
anything
we can
from your side, then
end here. We can
end
meet
here. We
again
can
next
meet
week.
again next week.
So
So
so if there's
so if this
if it is
if
all
it
fine
is
with you, so
all
we can
fine with
shall
you,
we
so
end this
shall
meeting.
we end this meeting?
Yeah, thank you as well.
Yeah, thank you as well.
Thanks
So
all for
thanks all for
joining
joining
this session.
this session.
So,
So
I guess like
I guess like we can
end it right here.
end it right here.
So we can meet
So we can meet
next time.
next time.
So
So
okay,
okay,
see you next week.
see you.